Okay, gotta go, Emerson. Emerson, are you there? Just remove the...
Hello, Professor. I'm here, Julio.
Julio. Thank you, Julio. I saw just Emerson here. In fact, I see Emerson, Magrin, Paulo Drus, and Bruno Silva, Mirella. Oh, no, I see more people. Okay. I wish to say, do you know if Gustavo is there?
Yes, I'm here.
Okay. By the way, tonight we will have the meeting of the Brazilian community on robotics that is part of Brazilian Computer Society. And I wish to invite all of you to be there, mainly the ones who have registered. I think almost we have about 80 registered, and 77 of these have registered in a combo way. So these ones, all of them have the right of vote in the decisions of that the community is going to take today. I wish to congratulate Federico. I don't know if you were in the in our musical event on Thursday night. I think your paper was the best paper of the conference. Don't know if you knew that. So just I saw you here. Congratulations.
I didn't know.
Okay.
Thank you very much.
And I think there are other people in here that with this paper, these best papers, in fact, 15 of the papers are going to be invited to be in the Journal of Intelligent and Robotic Systems, okay, to submit to this journal. Okay, I will start the afternoon section now. And I wish to invite Gustavo. No, sorry, it's Felipe. No, it's Gustavo. Thank you. For the first talk on performance analysis of relative GPS positioning as function of latency. I don't know if you wish to present the video or are you going to present straight yourself, Gustavo?
Could you please play the video?
Sure, Julio, please, could you do that? Okay.
Hello everyone, my name is Gustavo Carvalho. I'm a student in the Master's Degree Program in System and Automation Engineering at Federal University of LARS. And I will be presenting the work entitled Performance Analysis of Relative GPS Positioning as Function of Communication Latency. Here is how the presentation is organized. I will introduce the GNSS system, followed by the materials and methods, discuss the methodology, the results, conclusion and future works, and references. So let's start defining what is Global Navigation Satellite System. According to Kaplan, it is a self-position satellite system capable to provide accurate, worldwide, and three-dimensional position, velocity, and navigation information to users proper equipped. The first system created was the US GPS, operated by the US government, and it is open to the civilian public since 1995. And it quickly became the most dominant navigation system all over the world. Currently, there are 4 constellations in full operation capability that include the GPS, the GLONASS, operated by Russia, the Beidou, operated by China, and the Galileo, operated by Europe. And this kind of systems, they provide 3 types of measurements in order to obtain a final position solution. And they include the pseudo-range measurements, Doppler shifts, and carrier phase. In this work, we will focus on the pseudo-range measurements. According to the literature, the final position solution of the GPS lies on a range of 10 meters due to some sorts of errors affecting the position accuracy. There are 7 types of errors that can be classified in 2 modes. The first one is the common mode errors, that is experienced by all receivers in the same vicinity and in the same time frame. And they include the ephemeris error, the satellite clock bias, ionospheric and tropospheric delays. The second mode is the no common mode errors, and they are different for each type of receiver, and they include the receiver clock bias, multipath error, and receiver tracking noise. In order to mitigate the common mode errors, there are several approaches, and we can list 2 of them: the differential GNSS and the relative GNSS. These approaches are very similar, and both need a reference station equipped with a high-performance GNSS receiver in a surveyed location. And they are prone to 2 degradation factors, which are the baseline separation, that is the physical distance between the reference station and the rover, and this factor was studied in a previous work, and the communication latency, the main focus of this work. So the objective of this work is to study the effect of communication latency on RGNSS position estimation accuracy. And we want to provide a comprehensive analysis relating the maximum communication latency between reference station and rover, and the feasibility to obtain a RGNSS position solution at sub-meter accuracy level. The application and relevance of this work relies on the fact that multiple segments would benefit from more accurate position estimation at low cost, including the autonomous vehicles and precision agriculture. And the second example is highlighted because here in Brazil, the agriculture takes a huge place in the economy, and the agribusiness is expected to represent 30% of Brazilian gross domestic product in 2021. So this segment would benefit a lot from systems more accurate in order to provide position solutions. The materials and methods used are the Brazilian Network for Continuous Monitoring of GNSS Data. That is the most precise geodetic reference structure in Brazil, and it consists in 112 high-performance GNSS receivers installed in surveyed locations all over the country, as we can see here in figure 2. It provides GNSS raw data in 3 different ways: in real time, via any-trip protocol, in a daily post-processed GNSS data with track interval of 15 seconds, and also GNSS data with track interval of 1 second. And this data can be freely accessed at the IBGE website. So the relative GNSS approach consists of 2 receivers in the same vicinity, tracking the satellite signals containing the observables like the pseudo-range measurement, that is function of the true receiver position, corrupted by the 7 types of errors discussed previously. And the idea is to form pseudo-range measurements so that the common mode errors can be cancelled out in the subtraction process. So the single difference pseudo-range model can be expressed in terms of the distance between the reference station and the rover, and the remaining non-common mode errors, since the common mode errors were cancelled out during this process, subtraction. To obtain the position solution, the extended Kalman filter was used, where the state vector is defined as the relative position, the relative velocity, the relative clock bias, and the relative clock drift. The dynamic model is defined as the derivative of position is the velocity, the derivative of clock bias is the clock drift, and the derivative of velocity is 0, and the derivative of clock drift is also 0. For position estimation, daily post-processed GNSS data was used with tracking interval of 15 seconds for 1 hour, corresponding to 240 epochs, where 2 stations belonging to RBMC was used. The MGV1 was selected to be the reference station located in Virginia, and the MGLA was selected to be the static rover located in LARS. The state vector was estimated using the extended calm filter algorithm at each time index, going through 1 to 240 epochs, and with a value of latency L using the single difference pseudo-range measurements. The experiment was repeated for latency values of 0 to 100 epochs, corresponding to a delay of 1,500 seconds. To assess the performance, 3 criteria were selected, which are the individual channel position error, the horizontal position error, and the total position error, defined in equations 1, 2, and 3 respectively. For performance analysis, Figure 4 plots the root mean square error for individual channel position as function of latency for north, east, and down position. And as we can see, the root mean square error increases as the latency increase for all the 3 channels. Another thing that we should pay attention in this figure is that the root mean square error for east position varies in a smaller proportion if compared to the other 2 channels. It can be explained by the GNSS dilution of precision that describes the strength of the current satellite geometry on the accuracy of the data collected by the GPS receiver at the time of use. It means that smaller values for DOPs implies in greater accuracy in the final position solution. And as we can see in figure 5, for east channel, the DOP is smaller, almost 2 times smaller than the north DOP, and it can explain the greater accuracy for this channel. The mean error of horizontal and total position was also analyzed and plotted in figure 6, along with their standard deviation. And as we can see, for horizontal position, the error remains under 1 meter level at 1 sigma during all the experiment, with latency up to 1,500 seconds. And these values are summarized in table 1 for latencies of epoch 0, 40, and 100. For a brief comparison with another approach, the GNSS approach presented in the work of Farzana and Farrell is presented in table 3. And as we can see, the mean error for relative GNSS approach remains smaller, including the standard deviation and the maximum error value for all these criteria here in this table. And another outcome we can see is that as the latency increases, especially for the total position criteria, the standard deviation also increases, which implies that the uncertainty increases also. So after analyzing these results, we can conclude that horizontal position estimation accuracy is achievable at 1 meter level for 1 sigma, with latency up to 1,500 seconds. We also can conclude that RGNSS is effective to correct common mode errors, improving position accuracy. And also this approach proved to be more robust than differential GNSS in terms of latency sensitivity. For future works, our group intends to extend the same investigation of baseline separation presented in a previous work and the communication lattice effects in this work for moving platforms equipped with low-cost, multi-frequency, and multi-constellation receivers. Here are the references I used in this presentation. And I would like to thank you for your attention, and I would like to open the floor for any questions you have about this work. Thank you very much.
Okay, thank you, Gustavo, for your presentation. Nice work. Error estimation is always welcome. And I open here for questions if people from the audience or including YouTube. And here the Zoom have a question, please. You can make it now. Nobody from YouTube, Julio?
No, Professor.
Okay, and from here, okay, Gustavo, so if nobody asks, I should do it myself.
No problem.
I wonder if you do have tried with other approaches than the Kalman filter. I think the Kalman filter is the most indicated one in this GNS, right?
So far, we didn't use another approach because the Kalman filter is the state of the art and the best filter that, in this kind of application. And I think we will keep using this approach, but with different scenarios, like I said, with moving receivers and with different applications, like in farm or in a urban area. So these kind of changes that we will do, but the approach, it will be doing the same thing.
Yeah, that would be my next question. If the receiver moves, so this error is going to be a little higher or not?
We think that the accuracy will be affected by the moving receiver, and that's our next step. We already have a robot to do the movement, and next steps are going to be with moving receivers, and we will see how it will impact the final accuracy of the position estimation. But it's expected to be a little bit worse.
Okay, so and if it goes inside?
It probably will lose tracking, and another approach is the fusion sensor, like GNSS with inertial navigation, with encoders, and in the future we plan to make fusion sensoring with different types of navigation. This is only the first step.
Okay, I thank you very much, Gustavo. We are a little late, and very good work. And I think you have a lot more of contribution in this area. Go ahead and good luck on your researches in there.
Thank you very much. I appreciate.
Thank you. In the next, we will go to the second paper. It is on position control of omnidirectional robots through visual surveying by Pedro Figueiredo Assad and Raquel Esperança Patino. I ask who is going to present this work.
Good morning, Professor. Good morning,
Pedro,
everyone.
do you prefer to run the video, or are going to present it by yourself now?
Please, could you present the video?
Okay. Julio, please, could you put the video?
Hello, everyone. My name is Pedro Luis Figueroa Zaire, and today I'm going to present the project Position Control of an Omnidirectional Robot through Visual Servoing. This project was developed with Professor Raquel Patiños Cosina and presented in the Latin American Robotics Symposium. For the introduction, mobile robots are currently an important field of research with multiple applications. The classic drive systems as Ackermann and differential were the most used, however, they were limited by rotational movement. And with the appearance of the omnidirectional design, this autonomic drive allows robots to perform movements in any direction. Designing an effective navigation strategy for mobile robots is one of the most important issues in the field of autonomous robots. And for that, in this project is considered the visual servoing approach. The visual servoing refers to a control technique where data is acquired through a camera to control the movement of a robot. It is classified into position-based and image-based visual servoing. Then, for the image acquisition scheme from a camera, we follow the next steps. First, we identify an original image through a camera. Then we apply a pre-processing step, in which we apply a subtraction operation and a median filter. Then we binarize the image. And finally, we apply morphological operations, erosion and dilatation, in order to identify the 3 red marks of the robot and the coordinates of the center of each red mark. Then each coordinate identified has to be converted from pixels to meters, and for that we use these scaling equations. And then with the converted identified coordinates, we can also calculate the center of a triangle formed by the 3 red marks by calculating the mean value of the coordinates. And finally, we can show in the image the 3 red marks identified with the coordinates of the center of each mark, and also the center of the 3 points that it is also the center of the robot identified. Then, for the kinematic model of the robot, for this project, it was used a 4-wheel omnidirectional robot, and for that, the representation of the omnidirectional robot is shown in the omnidirectional robot layout. For this layout, it is required to identify the inverse kinematic model and the direct kinematic model. In the inverse kinematic model, the input vector will be the linear and angular velocities of the robot to obtain the angular velocity of each wheel. And in the direct kinematic model, the input vector will be the angular velocity of the wheels to obtain the linear and angular velocity of the robot. Then, for the fuzzy gain tuning scheme, we define 2 inputs that will be the error function input and the rate of error function. With both of these inputs have three membership functions, and then we define also the output gain with 3 membership functions. With these inputs and outputs, we define the inference table in which we obtain the 9 rules required for this fuzzy logic system. Then, for the image-based visual servoing scheme, we have here the general equation of the image of the visual servoing, in which the pixel velocity of one identified point, it can be estimated by the image Jacobian matrix and a camera velocity vector. But for this case, we identify 3 points, and for that we rewrite the Jacobian matrix into this expression that with 3 Jacobian matrices for each identified point, and then we can invert the Jacobian matrix in order to obtain this new expression in which the camera velocity, or in this case, the robot velocity, depends on the Jacobian matrix, the inverse Jacobian matrix, and a vector of the estimated image velocities of the 3 points identified. To calculate the estimated velocity of each point identified, we have to obtain the difference between the image point identified in the desired image and the initial image, and then multiply by a gain value. This expression is applied to form the error function matrix. In this matrix, or in this vector, each component will be the difference between the desired and initial image point identified, For that, this vector will have 6 elements. Also, we have to obtain the gain matrix, and each element of the gain matrix are obtained from the FuzzyTune system. And for that, we can propose the following control law, in which the camera velocity, or in this case the raw velocity, depends on the inverse Jacobian matrix, the gain matrix, and the error function matrix. Then, for the experimentation results, first we have the initial and desired image identified in this figure, where the blue triangle represents the initial image and the green triangle represents the desired image. And for that, we identify the 3 red marks and the center of the robot. Then we generate a trajectory from the initial and between the initial and the desired image. Each point, each new triangle and each new center of the robot are generated with the algorithm based on the image-based visual surveying control law proposed, and then it is forming this new trajectory until the robot reaches the desired image and also reach the desired position. And because in this figure it is shown that the robot reached the desired position, it is also shown that in the error function graphic, all of the error functions for each coordinate, each image point identified tends to be 0. Then we repeat the experiment by changing the initial and desired values, the initial and desired position, to generate 5 new trajectories. For each trajectory, we have to evaluate the total distance obtained between the initial and the desired position, and the total distance generated by the algorithm of the image-based visual surveying. And for that, we have this graphic of the distance error for each trajectory. In each graphic, for example, for the trajectory 1, we have the total distance desired and the total distance generated, and the difference will be the distance error. In this case, for trajectory 1, the distance error will be 0.002 meters. For the trajectory 2, the distance error will be 0.001 meters, and the same case is applied for the other 3 trajectories. Finally, for the conclusions and recommendations of this project, an image-based visual surveying control scheme was implemented to perform the position control of an original mobile robot, as well as a gain tuning based on Fuzzy logic to adapt these values during the process. Identifying multiple image points represents more computational work, and also the experiment was repeated with different configurations of initial and desired positions, and each trajectory obtained have an error of less than 1 centimeter. Then it is recommended to test this system with different omnidirectional configurations to compare its effectiveness, and also to observe the speed change of the system. It will be necessary to add and modify the membership functions of the Fuzzy tuning scheme. And this is all for the project. Thank you for your attention. Goodbye.
Okay, thank you for your presentation, Pedro. I ask if someone from the YouTube or from here have questions.
None from YouTube.
Okay, thank you, Julio. And from here?
I have a question, if I can.
Okay, go ahead, Federic.
Pedro, I like your work. I think it's really nice to work with omnidirectional robots. And I was wondering if it is possible, or you think about do the same approach of move the robot from one point to a desired position, but without a global localization, because I think you have like a camera doing some global localization, but if you can do something similar, but with the robot localization itself.
You mean with one point identified? the robot, for example, as a one point.
No, I mean like the robot not depending for a global localization system, and the robot estimating its own localization.
You mean like estimating the position of the robot instead of
Pedro, I think I can complete Federico's question with my one. Your application, I think you have visioned this for the robot soccer, right?
Yeah.
So take now the camera that is on the top and put it in the robot. I think that's what Federico is asking. Removing the camera and put it in the robot, how is it going to be? If you can use the same approach on image-based for in this situation where the camera is on the robot. Is that Federico?
Exactly. Exactly.
When the camera is on the robot.
Yes.
Yeah, I think it's possible to perform the visual surveying approach to control a robot, but you have to consider that if the camera is in the robot, then you have, for example, in this case, because the camera is on the top, looking to the robot, the distance between the camera and the robot, the height distance, it's constant in every case. But if the camera is on the robot, this distance will become another variable to control, to identify, and you have to consider this because the camera will have to look to the point that you want to identify, but this point will have an X coordinate, a Y coordinate, and also the Z coordinate or the height coordinate from the camera. As I said, because now the camera is on the robot, that height distance, that set distance or height distance will not be constant. So in the literature that I read, it explains that this is also another variable to consider if you try to do the visual surveying, or if you try to use the visual surveying in this case.
Okay, thank you very much, Pedro.
Okay, thank you, Pedro. And in which category are you competing, just to complete? In the very small soccer or in the small soccer of RoboCup?
Well, no, this project is independent from the robot soccer categories, but I would like to participate.
Okay.
Yeah.
Nice work. Very good. Thank you, Pedro. And my partner, Raquel, which has some work with us too. Okay. Nice to see you here. Congratulations
thank you
on the
very
work.
much.
And thank you. We go to the next work now.
Thank you very much.
Which is target detection using multiple foveas by Petrúcio Medeiros.
Hi, Professor.
Petrúcio, are you there?
Yeah, I'm here.
Do you wish to play the video?
Please.
Okay, please, Júlio, can you play the video for Petrúcio?
Hi, everyone. I'm Petrúcio Medeiros, and my work is target detection using multiple foveas. In real context, the robots must be able to find some target according to the task and react to some adverse event during its operation. But this requires runtime process, and this is a challenging task because to the data acquired. The operate environment of a robot contains a lot of visual information, and not all information can be processed at the same time. Then, the robot needs to select the essential information to perform the task. In this work, we build the visual attention process using the foveation technique. Inspired on biologic vision, this keeping some small region of the image at high resolution. and reducing the resolution according to the approximation to the periphery. Based on this idea, Gonçalves proposed by multi-resolution multi-features method that select parts of the image and resize them equally to smaller sizes. This method stands out for reducing the processing time in extracting information, but keep fixed fovea in the center of the image. Subsequently, Gomes formalized the multi-resolution with moving fovea method that provides mobility to the fovea. During a task, we have multiple targets in the image and need to keep the visual attention in each of them. In this context, it's necessary to move the fovea between targets. However, these movements are expensive and without guarantees that all targets will be tracked. Trying to solve it, we extend the visual system for support multiple foveas. Foveas is widely used in the literature, but there are few references that use the foveas to estimate the target position. We highlight this research because they use a local field potential with foveas to evaluate object displacement, but they didn't consider the weighting of multi-resolution levels. Thus, target detection in other multi-resolution levels is compromised. So, we propose a new approach to target detection using multiple foveas. Okay, the basic idea is to estimate a probability of target detection in each fovea, taking into account all resolution levels, and combine this information to find the target's position. Okay, but how do we do it? A robot task contains one or multiple targets. A set of features stored in the robot's memory represent these targets. The feature is a portion of the image that contains relevant information and it's encoded in a descriptor. During an operation, the robot matched the descriptors of the targets stored in its memory with those acquired by sensors. Matching descriptors results in false matches, the outliers, or true matches, inliers. So we combine these values into an inliers rate represented by equation 1. We use multifoveation to put foveas in the images acquired by sensors. These foveas have m levels. Each one is tracked features and has an inliers rate associated. But I don't know if the target is at all levels. For this, we propose a level weighting approach, where the level weights are given by the proportion of transformed pixels, defined by equation 2. And the linear combination of weighted levels and inlier rates provide a fovea detection function. It returns a maximum value when the fovea is in the center of the target, and this value decreases when we increase the distance between the fovea and the target. This linear combination generates a detection surface through successive movements of the fovea by the image. But this procedure has a high computational costs. Thus, instead of moving the fovea by all pixels in the image, we code using space around the x and y axis, but this also requires a lot of processing, and the second possibility is keep fixed fovea at strategic points in the image. Okay, we use the last one possibility and we subdivided the image into 4, 5, 6, and 9 regions. In each subregion, we put a fovea. Furthermore, we propose two methods that move the fovea using interactive mode. We propose they use this information in methods based on gradient descendant, maximum likelihood estimator, multilateration, trilateration, and weighted variance coordinators to estimate the target position. The local gradient is calculated by the difference between the central fovea and the neighboring foveas. The region reduction method reduces the search region according to the direction to the local potential field. The local gradient intersection method indicates an estimative of target's position according to the intersection between two local gradients. These methods make use of three possibilities. The first one uses the 8 positions around the fovea. The second possibility uses the 4 positions up, down, left, and right. And last one, use the 4 diagonals. Okay? The detection surface converges to a multivariate normal distribution, where the mean represents the target position. For this, we can use the maximum likelihood estimator. In these methods, we interpreted the detection of the fovea as a circumference that increases when the detection value decreases. In other words, there is an inversely proportional relationship between radius of the circle and the detection value. These methods estimate the target position using the intersection between the circumferences. And for that, they need information about the distance between the foveas. This method implements an interpolator that uses 3 foveas to estimate the target position. We select 3 foveas according to their proximity and maximum detection values together. We weighted their position using their target detection values. We used the toy video for visual tracker benchmark to validate our theory. This video contains a sequence of 271 frames under scale variation, fast movement, and rotation of tracking time. The target was extracted from the first frame of the video, and we use foveas with 4 levels and surface. In our results, we calculate the mean error using the Euclidean distance between the estimated positions and the center position of the ground truth region. These results demonstrate that the mean error of local potential methods are greater than 76 pixels, and there is a scattering of errors generating a high standard deviation. This information indicates that the methods may not converge to target position. These results show that mean error of estimated position by multilateration, trilateration, and barycentric coordinates are most accurate than maximum likelihood estimator. Furthermore, we can observe that the standard deviations of the multilateration errors for the 4 settings show little variation because this approach uses all fixed foveas to estimate the target position. Our conclusions we propose a new target detection approach, exploring several mathematical strategies in this work. We conclude that the trilateration, multilateration, and barycentric coordinates perform better compared to local gradient and maximum likelihood estimator. We can detect the target position using at least 3 foveas, and in future work, we will study the multiplicity of identical or similar targets, target absence, and real-time application. This is my reference, and thank you.
Okay, thank you, Julio, and thank you, Petrúcio, for the video. I will open for questions now. Someone from YouTube? No questions from YouTube?
No.
From here?
I have a question for Petrúcio.
Go ahead, please.
Because if I see that a future work will be a real-time application, and I would like to know if the processing for a real-time application in a mobile robot will be possible or not.
Hi, it's possible to have an application in real time, but we don't explore this application. But in future works, we have tried to put this application in real time. And during my master degree, I put multiple foveas and processing in real time. And this application was generate a publication, and we share with you if you want in the next presentation. Okay.
Okay, thank you, Petrúcio. The last this experiment setup that you did was with the fixed camera, isn't it? Like and you move the object you want to track. But if the camera is on a robot, which the robot is moving and trying to like the target of landmarks, do you think, and maybe moving landmarks, you think also is possible? I think yes, but I don't know.
It's possible. It's possible.
Okay.
It's great. It's a great question, and it's possible because the structure is have mobility, and we can configure the positions of the foveas within the image. So I don't. It's possible to try to do it.
Okay, thank you very much.
Thank you.
Thank you, Petrúcio, for your answers. Thank Frederic for your questions. I will move up and call our next presenter, who is Federico, right, Andrade?
Yes.
Active localization of mobile server robots in symmetrical and open environments. I wish to say that this is our best paper of LARS. Before you start, congratulating your team, Federico. Go ahead. If you wish to put the video.
Yes, please.
Okay, please, Julio, can you play the video for us?
Hello, welcome to the presentation of the work Active Localization for Mobile Service Robots in Symmetrical and Open Environment. My name is Federico Andrade. I'm with de Facultad de Ingeniería, Universidad de la República, from Montevideo, Uruguay. The outline for this presentation is a brief introduction, the problem statement, active localization system overview, then the experiment results, and the conclusions. Well, improving robot localization will lead to more secure, robust, and efficient robots. For indoor areas like hospital, houses, where global localization systems that not perform correctly, there is still some room to improve with active robot localization. The research questions which active localization want to answer is where to go and where to sense in order to improve the localization. Well, the problem we are addressing in this work is a robot in an indoor environment. We want to solve short-term active localization on symmetrical and open areas. The initial position of the robot is known, so there is a position tracking problem, and there is a path which is given by the mission planner. The map is represented as a two-dimensional occupancy grid, and the robot we are working with is a differential drive equipped with a laser rangefinder with a field of view of 70 degrees and a distance perception of 8 meters, and this laser is fixed to the frame of the robot. I'm going to show first the intuitive idea from this algorithm. So when the red arrows, which are the particles, spread away because of the robot movement, we cluster the particles, and from each cluster we find a representative particle, which are the gold arrows, and these gold arrows are set in a common fixed frame. You can see that in the middle image. So there we build a compound map, which the map from each of the representative particles. So the black points in the grid map are the points where both representatives vote that are occupied. The more clear points are the points where both representatives vote that are free. And the gray are cells which one representative vote that is free and the other representative vote that is occupied. And that are the cells we are interested in, because we want the robot to sense these cells to gain information, so the wrong hypothesis or the wrong particles will disappear, and the system will keep the best localized ones. So in this compound map, the more close to the robot point is selected, and then the robot rotates to sense it. And in the last image, you can see the robot after rotate 90 degrees to the right, and you can see how the upper cluster became smaller, and the other one became more focused. So the system overview, you can see it in this image. The main component are the blue boxes. The first one has as input the particle cloud from MS Monte Carlo localization. Then in this node we cluster the particle cloud and find the representative, which are the output, and in the second node, in the blue one, which is in the upper right, we took as input the representative, and we generate this overlapping map, and in that map we find the candidate cell. So the output from this module is the candidate cell, and there is a last module which is down in the right, which takes this candidate cell and find the commands for send it to the move base, for move the robot and sense the cell we want to sense. We did some preliminary experiment and we found out that we can't build the compound map with all the particles because the time of processing that map increased dramatically. For example, with 1000 particles, you have to wait 1 minute to have the compound map. Spectral cluster and K-means are proposed in this work because both have good performance finding clusters in this kind of formations. And all the cells in the compound map are within the range of the robot sensors. So only with rotational movement the robot can sense the cells which will discard more particles. So to end this section, I want to show you a flowchart of the system. So the robot is following a path which is given by the mission planner. Then if it can find at least 2 clusters, then publish the representative from each cluster, build the compound map. In the compound map, find the most informative cell, and then rotate the robot to sense that cell, and then continue following the mission. Well, we did experiment in simulation and real world. We evaluate ground truth and localization uncertainty. 4 agents were used: passive localization, which is Monte Carlo localization, active localization using the scan clustering algorithm, and then the active localization with K-means and the active localization with spectral clustering. With both are our proposal. 10 runs with each agent in each environment, both in simulation and real environment. We used Turtlebot 2. Everything was fully developed in ROS, and the particle cloud size was 2000. Well, these are the simulated scenarios. Here you can see the waypoints given by the path planner. In the first case, in the left case, we have the one here, and then go all the way down, and then back to the right, to the left, to the right again, and finally goes up. And in the other case, start in the upper right, go all the way down and up and down again, finally enter in the room and go outside. Well, in the first environment, in the office environment, the spectral clustering and K-means had a better performance than the other agents. In particular, K-means keeps the ground truth error smaller, less than 10 centimeters, and also keep the dispersion smaller than the other agents. And in the second environment, which is the symmetric one, both spectral clustering and K-means have the smaller ground truth error, and also keep the dispersion smaller than the other agents. This is a real scenario. Is the floor 0 of the Instituto de Computación. Here in the right you can see the waypoints followed by the robot, which are at first go to the left and then go to the right, go up, go down in a diagonal, and then go up again. Also, you can think as the service robot is searching for some object or tidying the house. And then here only 4 experiments were done, only just for confirmation of the result. And here we can see again that in real experiment, spectral clustering and K-means with this strategy of building a compound map and sensing the point, keep the ground truth error in around 13 and 14 centimeters, and also keeps low the dispersion. So as conclusions, this work presents an active localization system for the position tracking problem. The system has been oriented toward managing indoor environments with open areas and symmetric spaces, which are the most problematic ones. This experiment showed that the development system decreases both ground truth and pulse uncertainty during the robot mission. And finally, we are working in an active SLAM algorithm using this proposal as a front end from the mapping algorithm.
Okay. I think you are done, right, Federico? Yes.
Yes.
So I think we still have time for one question, please. If someone wants to ask something, congratulations for your work.
Thank you very much, Chris. I'm very proud about what you said about our work.
If no one asks, so I will make you one question. By the way, I knew that corridor of UDLAR. I think I knew it. I went there in 2013, 2014, I don't remember. You are dealing with grid maps. Do you think your work can be extended if you go to 3D? I mean, 3D grid maps?
Yes, I think you can.
You have voxels in this
Yes.
case, right? Instead of you having planar squares.
Yes, I think the same idea can be extended to, yes, there are like 3D grid cell maps and also voxel maps. Yes, because you just need like a different estimation about your pulse, then build this compound map from, if you have like a few estimations, you can build it from all the estimation if you have, or if you have too much estimation, you can build the map with previously clustered. And the idea is the same, because in the 3D map, you will have voxels or cells from the 3D map with X, Y, and Z coordinate, which will be the cells which give you the more informative information, and some of the particle or some of your hypotheses will be discarded by looking at the cells, and the other will be improved.
Okay. Of course, in this case, the processing will be much higher. Then you
Yes.
would perhaps need another kind of processor, an embedded board, I don't know, right?
Yes, the processing, it will be, yes, increased. Maybe I didn't use a GPU in this case, so maybe you have to access to a GPU, or maybe use a reduced map, like small cells all around the robot. But
Okay.
I think it's a nice idea for drones, for example.
Yeah, I
which
thought
move in a
about
3D
drones.
space. Yes.
Okay, very nice work, Federico.
Federico,
Sorry,
sorry.
Bruno. I
Luis,
took 5 minutes from your time, Petrus. I have to pass now to Bruno in order to keep the schedule. You can make questions for Federico in the breakout rooms. If you wish, you can go there and talk, okay? Thank you, Bruno. I invite you now to assume the next session. And again, sorry for that, taking 5 minutes.
Okay, thank you, Luis. We are a little bit behind the schedule. We are starting at 3:05, but I don't think there is a problem. Well, maybe there is a problem, but let's keep going with the session. So now we start vision, sensing, and mapping session number 5. I'm Professor Bruno Silva, and I'm going to be the chair of the session. The first work to be presented is by Nelson Traversi of Federal University of Rio Grande. And the work is entitled VBM Granulometry for Real Applications in the Fertilizer Industry. So Nelson, you there?
I'm here.
Hi, Nelson.
Can you play the video? I'm having
sure.
some problems with my internet right now, but...
Okay, no problem, Nelson.
Hello, my name is Nelson de Faria Traversi from Federal University of Rio Grande. I'm here to present the paper called VBM Granulometry for Real Application in the Fertilizer Industry. This study started with the search of new alternatives for the sieving process used in the fertilizer industry, seeing as those methods have a high time consumption. With the computer vision techniques, the particle size analysis could be faster, with reduced costs. However, computer vision techniques have problems segmenting images with no background. On top of that, the factory floor will introduce a new problem in the form of the noises, due to the movement of the grains in the conveyor belt, dust, and illumination. This work will explore the effectiveness of 4 deterministic methods to segment images and the effects of possible noises present in the factory floor. In the fertilizer industry, one of the quality controls done is the measurement of the size of the grains of fertilizers. Grains having the diameter between 2.36 and 2.80 are considered the ideal for mixing with the soil. Grains with a diameter bigger than 2.80 will be too coarse to be properly mixed with the soil, and grains with a diameter smaller than 2.36 will be too fine for the same purpose. So, due to this fact, the factory needs to constantly calibrate to maximize the yield of this diameter range. In order to verify the current production, samples are taken from the production line and sieved to determine the current production status of the factory. The following algorithms were chosen because they already been grounded in this area. Watershed uses transformations in grayscale and region-based techniques, treating the image as a topographic map. The brightness represents its heights, using it as a center and find the lines that run along the ridges. Keen edge detection is an edge detection operator that uses multi-stage algorithms to detect a wide range of edges in the images. K-means is a clustering algorithm used to segment an interest area from the background. Otsu performs automatic image threshold, separating the image in 2 classes, foreground and background, allowing to disregard the partial grains too obscure to be seen and highlighting the frontal grains. This work intends to study the impact of factory noises in those methods. In order to properly evaluate the methods mentioned, a large representative sample of data properly annotated is needed. The collection of data of this species on the factory floor is nearly impossible with the resources available to us at this time. So an image simulator previous made by us was adapted to include various noises in increasing strength in order to study the impact they made on the deterministic segmentation methods chosen. This simulator uses photos of individual grains, like in the picture in the left, properly measured to generate a surface fully covered, like in the picture on the right. At the same time, it generates a colored image A. It generates a perfectly segmented image of the image A, and also documents the percentage of each type of grain present in the top layer. After this, the image distortion noises are applied in several copies of the image A, in increasing degrees. For the noises used in the simulation, we choose to represent dust, blur, and gamma, as those are the most critical distortion noises present in the factory floor. Starting with dust, one of the main problems we face in the fertilizer factory, it occludes pixels in the image being captured and can interfere with the camera lens, make it lose parts of the information. A similar distortion chosen to represent it was salt and pepper, a noise that can occlude and interfere with the image in similar matter, altering different pixels. Due to the constant movement of grains in the conveyor belt, we choose to use blur noise to simulate this effect of movement. In order to study the impact of insufficient illumination or excess of illumination present in the factory floor, gamma filters were applied. Regarding the intensity of the noises, salt and pepper had the total percentage of the pixels modified by the noise being equal to the intensity value times 100. In the blur filter, the windows that blur the image had its size determined by the value of the intensity times 10, going from 1 to 5 pixels. In the gamma noise, the values of the brightness were increased or decreased by the values of the intensity. This simulation uses noise values sometimes above the real conditions. This was made to see the limits of the deterministic methods in the worst-case scenarios. The experiments were carried out using 1200 images containing most ideal grains, 1200 images containing mostly coarse grains, and 1200 images containing most fine grains. Each of those images was treated with noise filters of different levels, varying the degree of the intensity by 0.01 up to 0.5, generating 158,400 images with noise. In order to evaluate the results, the region on the image segmented by the deterministic methods and segmented image by the simulator are compared. The region of each identified grain is measured with its region props from SkyImage, comparing the total number of grains identified on each surface with the ground truth. We can see the error present in the images without noises and also the effects of the noise in each segmentation. The analysis of the general absolute error was done in two parts. Initially, the average error between the equally mixed groups were analyzed, and in a second instance, the error present in the fine, ideal, and coarse groups were analyzed, in order to identify which noises are most harmful for each group. For the mixed group, the lowest error obtained in all methods was the Otsu, getting 12% error in a clear image, but on other hand, the error due to salt and pepper skyrocketed at the beginning, reaching 40% error with 20% of pixels modified. When the salt and pepper noises reaches 40%, the global error was lower. The sudden drop in the error is due to the fact that coarse grains are identified as fine grains, and coarse grains are being identified as fine grains. Since the comparing method compares the number of identified grains in each class on the RGB file and in the segmented file, the error appears lower than it is. In most cases, when the gamma filters brighten the image, there is an improvement in terms of quality until the filter passes a threshold of the intensity of 0.2. After that, the mean error starts to climb up past the clean image error in some methods. Lowering the bright using gamma didn't affect much on the border detection. Blur was a special case. It remains stable with a blurry window of 1 up to 5 pixels. Anything more than that, the error goes up to 100% almost instantly. Analyzing the group with images containing increased quantity of fine grains showed that K-means have the least amount of error in clear images, reaching only 8%. The error related to salt and pepper in this method have a linear climb along the increase of the noise intensity, peaking at 35% error when 40% of pixels are corrupted, similar to the mixed groups results. With the use of blur and the gamma variations, it was possible to obtain error results of 5% using intensities of 0.1 up to 0.2, showing that in small grains, those noises end up being beneficial to the segmentation. In the watershed method, salt and pepper reached higher levels of 40% error when the noise affected 5% of the pixels. Analyzing the results of groups containing images with grains of predominant ideal size showed that K-means and Otsu had a similar lower error in the range of 7% up to 9% respectively in clear images. Using the gamma filters at lower intensity, either by brightening the image or darkening it, it was able to improve the accuracy of K-means method by reaching 96% accuracy. The salt and pepper filter had linear climb, peaking at 36% in the K-means method, and the blur filter had results similar to the clear image. Analyzing the results of the group containing images with grains of predominant coarse size, the highest error rate was found in the clear images. The lowest value found was 17% in the Otsu method, while it reaches the highest point of 38% in the Kane and 26% in the K-means for clear images. This high error rate is related to the fact that large grains are identified as several smaller grains. Due to the effects of salt and pepper noise, this error was reduced to 8% with the intensity of 0.2. Since the random corrupted pixels served to stop part of the segmentation in the large grains in the K-means method, while it reaches 40% error in the Otsu method. The blur and the gamma noises also improve the classification of the images, reaching error rates of 5 up to 10% lower than the clear images in watershed and K-means. Comparing all methods and using the same calibration, not one of them had the satisfactory error rate in all groups. Using specific calibration and filters, it is possible to increase the accuracy for one specific group, while it worsens the accuracy for the remaining groups. For the noises present in the study, salt and pepper had a linear impact in most groups, breaking up big grains, making them be identified as several smaller grains, and agglomerating smaller ones into big grains was some of the predominant effects observed. For most cases, the gamma filters improve the segmentation a little, showing that there is improvement to be made in the image capture, regulating the illumination. The blur filter had the biggest impact in how experiments. Any image with a blurring window bigger than 5 pixels would reach near 100% error rate. This problem is related to the fact that blurring window would be bigger than the border of the grains, to the point of overwriting it with softening effects. For this reason, the future works will explore the use of neural networks to segment images groups of grains of mixed size in fully covered images. I like to thank CNPq and CAPES for their support in this research.
Well, thank you very much, Nelson, for your presentation. I'd like to see if is there any questions from YouTube? No questions. Is there a question from the audience? Oh, Professor Todd, please go ahead.
Yes. Okay. Good afternoon. Congratulations for your work. I have a question. How do you deal with partial occlusion of the grains? Because you compose an image, and how do you deal with partial occlusion? Because if you are analyzing the size of the grains, if there is some occlusion, maybe you think that the grain is smaller than it is in reality.
The simulator generates a RGB image, a segmented image, and also give us a matrix containing the ID of each pixel and the information of each grain. So you can see if there are grain with too much parts of it occluded, and you can exclude this from the information of the ground truth. If a great part of the grain is occluded, 90% of the grain is occluded, we can exclude them.
Okay, understanding. The simulation, you have the ground truth. But when you migrate to a real application, how do you think that it will be possible to deal with this problem?
We still work with the top layer, and the layers underneath will need to be extrapolated, or we only work with the top layer initially. It's a great problem.
Okay. Okay, thank you.
Nelson, I have a question too. It's more of a curiosity, actually. So nowadays we have all these work with neural networks and deep learning and so on. And then you decided to invest in classical image processing techniques. So, well, my curiosity is, why in the first place did you choose to invest in these classical image processing techniques?
I wanted to see if it could be done with this method. Now that it is proven that it don't work, or if it works need for one special case, we're going to try neural networks. There are some works that use neural networks to analyze the minerals, bigger ones, and from there it chooses to use one of those methods. So they use the neural network to do a classification, then use those methods to segment it. So I wanted to try and see what could be done with the traditional methods first.
I see. Well, since you mentioned that you have the simulator that generates images for you, if you are confident enough in the generated images from the simulator, maybe if you think these images are good enough, then I think you have pretty much everything that's needed for deep learning techniques, and maybe build a constructed. Well,
it's the next step. It's the next step.
I believe it is. Okay. So, and do you have any other questions from the audience? Okay. So, Nelson, thank you very much for your presentation.
Thank you to be here. And
well, so now I'd like to call the next presenter, which is Professor Paulo Dreus Jr. Professor Paulo Dreus is going to present his work, water classification based on underwater monocular imaging.
Everson is here also, Bruno, the first author.
Oh, okay. Sorry, Professor Paulus, because in our programming, it was said that we're going to present, so it's going to be Everson then. Is that correct?
We will present together. We are here.
Oh, okay. Nice, very nice. Go on, please.
But go ahead with the video.
Hello, everybody. My name is Paulo Drius, and I will present the work developed with the students Everson and Ed Wilson with title Water Classification Based on Underwater Monocular Images. So, the summary of the presentation is a short introduction. After we'll talk about related work, methodology, results, and classification. The introduction is underwater robots operating in several types of water, and it's important to know the type of water in order to know restriction about the operation of these vehicles. Gerlov proposed in 1976 a water type classification based on the optical properties of the water. And they do the division in oceanic and coastal water, 5 types of in each one. Here you have the classification of the Gerlov water types. You can see here in the top with Roman letters the oceanic waters, 5 types, and here the coastal one. We have also 5 types of waters. And here in this dimension, we can see the water depth and the variation of the color in this situation. The objectives of this work is classify the water types, assuming a real forward-looking underwater images. The idea is to propose a simple and effective method using just the color channel of the images with no training set. We assuming that it's very hard to have a data set or a large data set with ground truth. So the idea is not using any training set. And also one objective is to estimate the water depth of the scene. So the related works, here you have some related works. We have the Uplavlink work in 2019, where they do a water type classification based on CNN model. In fact, Uplavlink rearranged the Gerlov waters, the 10 types of Gerlov waters into just 6. We also have the work of Berman in 2020, where they do Gerlov classification based on underwater image restoration and gray world assumption. Here you have the water Gerlov types proposed by Uplavkar, where they clustering these types of water in just one, since they are very similar, and these 2 types in just one type. And here the coastal waters 1 and 3 in just one type. Also, we have the related works of Beckerman in 2020, where they propose a robust estimation of the attenuation and dispersion coefficient, but they do not use the Gerlov classification. Also, we have the work of Vaz Jr. et al. In 2020 in LARS, where they propose the water classification using optimization search based on Gerlov coefficients. The methodology, the proposed methodology have some input data. The input data is one image, a single image, with different resolutions, different orientations, and different file types, and also a table with all water types and depths between 1 to 50 meters. The method initially estimates the average of the image in the RGB space. It allows the method to estimate the dominant channel, or the red, or the green, or the blue channel. After that, we do a clustering of the image pixels based on k-means algorithm. In order to find the k, we use the elbow method. And this clustering is just based on the RGB data. We don't use spatial data. The output of this is several clustering, k clustering, k clusters with the center and also the pixels. Here you have some input images example, where you can see here the image and here the cluster. You have 4 clusters in this case, the red, the green, yellow, and also the blue here. If the case of dominant blue images, we have a more specific method that initially discard inept clustering. After you see if the average of the image is a good estimation in order to select the cluster. In order to see suitable cluster, we evaluate the blue center of the clustering in terms of the average, and also see if this blue center is larger than the green center. The selection criteria to see if the image average is a good metric, we use HSV space, where we use the S in this HSV space, and also the red channel, if the average of the red in the image is larger than 175. It's useful for large scenes. Here you have some example where you have a large scene and the average is not a good estimation. So in this case, we do the discard based on the HSV space. Here we do the discard based on the red channel. Here you can see you have a very light image that it's very hard to estimate, and the average is not a good measurement. So if the average is discarded, we choose the water clustering, use the highest blue-red ratio, and if the average is not discarded, we choose the water searching each cluster in this weight, double, and we just select the cluster with lowest value in terms of this weight, double. Here you have again the image, the algorithm of the dominant blue images. For the case of dominant green images, we just select the highest or the biggest green clustering. If the green channel, the average of the green channel in this case is larger than 150, we discard this cluster. If no, we select this cluster. The dominant red image is also similar. We just discard the largest red clustering and discard the smallest and pick up the second smallest clustering. In this case of dominant red channel, it's just useful for type 7 and 9 in Gerlov classification, and usually it's a smaller depth, water depth images. Here you have one image of the dominant red channel. We also propose one object-free region optimization for the water clustering. It's based on standard deviation for each color channel. For this, we remove all pixels with more than one standard deviation in at least one color channel relation to the center. The estimation of the new average of the center average is achieved using the cluster after these discards. Here you have one example of one image and also the clustering of water. Here in brown you have the discarded pixels. You can see here that you discard this area and also the fishes. Here you also have one example. In this case, the discarded are in red color, and you can see here that you discard part of the diver. When you use the dataset swim, in this case, you have the segmented masks of the water cluster, so that method is not useful. In this case, but it's also required to do object-free region optimization, since you have this, for example, this area that you have the just a reflection of the water surface. After that, we do the classification based on Euclidean distance, and you just search the lowest value D in relation to the Gerlov classification based on type and depth. In order to estimate the depth, we choose the largest column in the water clustering and select the center of this line, this column, and compare it with all depths in the Gerlov classification. Here you have you have the line in the water clustering, and you estimate the depth for the center of this line. Here you have some results. We proposed a new data set with 89 images of all water types, and all images are manually annotated by 3 persons. The quantitative results that you achieve, we obtain 70% in accuracy and around 90% in accuracy. It's much higher than estimated using the VAS method and also the Berman method. Here you have some qualitative results in ocean waters that you can see the water type and the depth. Here another qualitative results. Here qualitative results in coastal waters. You have water type 1 and water type 3. Here water type 9 and water type 3 here. Here is the water depth, and here is the distance between the Gerlov classification and our algorithm. Here you have more coastal waters. Here you have some fail cases. We have these 2 cases. They are inappropriate images due to the camera orientation and no object-free regions. Here you have fail cases where you have problems with the light source and the images with closest average in at least 2 channels. The conclusion propose a new simple and effective approach to underwater image classification, and we achieve highest accuracy in related to the state of the art.
Thank you, Professor Paulo Dreus, for your presentation. Very nice work. Very interesting, very innovative too. I ask now if we have questions from the audience. Okay, no questions from YouTube. No questions from Zoom. Oh, Professor Paulo Dreus, I have a question. As always, I'm curious. How do you plan to use the estimated depth from these images? Is there an application in sight for this?
Yes, there are many different situations where we have an underwater robot and we do not have any sensor of depth, and we can use the image to get one estimation of that. And the idea is to try to fuse this information and an extra information and fuse it with classical sensors, for example, acoustic or pressure sensor, and give an extra information. But if you get, usually we get several videos from divers, and the divers do not have any idea about water depth. We don't have any information, just the videos. And the idea is to have a kind of tracking of the depth using this source of data that can be interesting, for example, for help diving or any kind of assistance to diver. That's one possibility, one room that open with this kind of visual-based technique to estimate depth, but not classical visual depth. That's the distance from camera to target. It's the water depth, the weight of the water column.
Yes, Professor Luis Marcos Gonçalves is commenting here in the chat that underwater images are always difficult to deal with. So that's which makes this work even more valuable. So do you have any other questions? If not, I have another question that I think Professor Luis Gonçalves is also interested. is because do you think this method can be used to, for example, estimate the quality of the water? I mean, in terms of pollution, of water pollution?
Yes, let's see. We are estimating the depth based on kind of standard metrics of water colors. And if the color diverge from that, there are several sources of reason to this phenomenon to happen. So we can measure the normality of the water using this kind of technique and how the water diverge from a kind of expected behavior of the water. It can be, for example, for excess of raining. It can be for a kind of pollution. It can be for we call HABs, that is growing of microalgae, and different environmental behaviors that happen. Yes, this technique can be used to monitoring water normality, not exactly pollution or measure pollution, but identify a kind of normality in the water. It can be an interesting tool for that.
Okay. Julio is asking if there is an ideal angle pose. Julio doesn't mention, but I believe he's referring to the camera, maybe?
We are assuming that you are doing forward-looking image. The idea is looking forward. The idea is to have water mass in the field of view of the camera. The camera can be inclined for down, for example, but we need to have water mass, because in some cases you have like bottom looking camera that you just looking for the seafloor. And in this case, we don't have any idea about this depth, and we lost our assumptions. But if I have one image that have targets or objects and also the water mass, we are able to estimate in a very accurate way. Using standard methods, not using deep learning, because in this application, it's important to highlight, it's very hard to obtain annotated data set and the quantity of data that you need to achieve good results.
Oh, that's a nice observation. So, well, do you have any other questions? Okay, so no more questions. Professor Paulo Dreus, thank you very much for your presentation.
Thank you, guys. Thank you.
So now I will call Mirella Mello from the Federal University of Pernambuco. Mirella is going to present her work, Occupancy Grid Map Estimation based on visual land and ground segmentation.
Yes, could you please play the video?
Sure.
Thank you. Hello, everyone. I'm glad to present the work Occupancy Grid Map Estimation based on visual SLAM and ground segmentation. Regarding autonomous mobile robots, it is possible to highlight three aspects: perception on mapping, location, and navigation. A powerful ally for more robotics autonomy is the SLAM algorithms, representing an intersection of mapping and location. Among visual SLAM classifications, the feature-based method associated with a sparse mapping gives a real-time system which is capable of detecting loop closure and doing optimizations both in real time. All of this combined with accurate location data. But concerning the mapping stage, the sparse point cloud represents a disadvantage for navigation tasks. Based on that, our proposed solution consists of a module that allows a link between this visual SLAM and navigation tasks, prioritizing low computational costs both for memory and performance. We propose this link by transforming the sparse mapping into a 2D occupancy grid map. The related works can be divided into two categories, which are works that developed an appropriated map for navigation given a sparse point cloud, and a second category that uses a dense point cloud. For now, I will focus on a particular one, which is the open source project RTab map, used for comparative purpose. It can build a 2D OGM with data from a stereo or RGBD camera. Specifically about the 2D OGM generation, the dense point cloud is divided into voxel, and for each one, a plane fitting is performed. Given the plane's tilt angle, the Vox is classified as a free or occupied area, followed by its projection into the 2D grids. Additionally, a ray tracing option can complement the map. Our approach uses a similar flow. However, instead of using a dense point cloud, we directly use the sparse point cloud generated by the SLAM system, resulting in a reduced processing time and memory usage. Another main difference is that our approach defines free area based on a two-dimensional search, avoiding three-dimensional data computation. Here, we can see the workflow of our proposal. Initially, image and camera parameters are inserted into the feature-based SLAM. We adopted the open source project called OpenVSLAM to provide location and mapping. An image frame is only inputted in the image segmentation module if the SLAM system defines a new keyframe. Subsequently, the entire sparse point cloud and the segmented image go to the cloud segmentation module. Lastly, the 2D OGM generation module receives the segmented cloud, the keyframes pose estimation, and the keyframes features in pixel coordinates and their respective 3D coordinates. To achieve a segmented image, first we calculate a disparity map using the same global mapping technique and its respective V and U disparity map. V disparity concerns a histogram based on the lines of the disparity map, while U disparity considers the columns of the disparity map. They review obstacles as horizontal lines and the longitudinal profile of the free area, as shown in the figure at the top. Next, it is necessary to filter the V disparity map. This is, remove every dot not related to the ground. The filtered V disparity map is modeled by B-splines curves, in our case a combination of 5 cubic splines, each for 5 segments of the V disparity image, as shown in the image. And parameters are estimated by the least square method. Finally, the image segmentation is completed by verifying every pixel of the disparity map D. If a pixel AJ belongs to the model B-spline function at J, then pixel is categorized as free area, otherwise as an occupied area. Once we have a segmented image, we can extend the segmentation to the 3D point cloud data. Feature and the respective 3D point located at the free area are defined as floor, otherwise as non-floor. The segmented point cloud is updated whenever a new keyframe is inserted into the SLAM system, which is the moment that new points are added or removed to the cloud. At this point, we have the sparse point cloud from the SLAM system, the segmented image, and the segmented point cloud between ground and non-ground. The entire non-ground point cloud is used to form the first OGM layer, which indicates only occupied area. Among the ground points, each point observed by the current keyframe form with the current pose estimation a line, represented by a distance value. We assume the set of distance value follows a normal distribution. Thus, outlier removal is performed based on a superior threshold calculated as shown in the equation. The remaining ground points are used to apply ray tracing projected into a secondary OGM. This is a layer containing only potential free grids. The final map is resulted from overlapping the two layers, and in case of conflict, the obstacle grid prevails for the sake of security. For evaluation purposes, we recorded 3 real environment scenes and a large synthetic one, as illustrated in the pictures. In 3 of them, we extracted the map ground truth. This is the configuration we used to compare our method, SegFloor, and RTab map. It is inputted for both the odometry data from OpenVSLAM, the image pair from a stereo camera, the robot frame transformation, and camera parameters. To our strategy, we also input the sparse point cloud from the OpenVSLAM. You can also see a brief overview of each strategy. For those scenes with ground truth, here are the results of maps overlay. The area highlighted in pink represents incompatibility between generated and ground truth maps. Therefore, the less pink color appears, the better the map quality. Maps from SegFloor and RTab map with the ray tracing option demonstrate a big intersection in most navigable areas. In Hall 1, the passage was noticed. In Hall 2, the obstacle was detected. In a synthetic environment, pilasters and other objects were also detected. For these environments, it was possible to calculate precision and recall using a probabilistic roadmap. Precision metrics are calculated by comparing the probabilistic roadmap generated over the estimated map and replicated on the ground truth. The table brings high values for the map's precision for both strategies. This is expected when visualizing the maps overlaid, given that most of the free areas coincides. In this way, collisions are hardly expected. We also use the recall matrix to define how much of this estimated free area represents the entire free area of the ground truth. This is, the recall represents map coverage. It is calculated by comparing the probabilistic roadmap generated over the ground truth and then overlaid over the estimated map. Again, the table shows high and competitive results between SegFloor and RTab map. The synthetic environment has an area of almost 700 square meters and a trajectory of 138 meters. It was also used to validate our technique in long term. The figure on the left reports the memory footprint over the number of map updates. It is interesting to note that using OpenVSLAN associated with RTab map is practically equivalent of having two SLAM systems running in terms of memory consumption. On the other hand, changing this configuration to OpenVSLAN, followed by our proposal, represents slight offset regarding the SLAM's memory footprint. Regarding the processing time over map updates in the figure on the right, the trend lines highlights an almost constant behavior of our approach and an increased behavior of RTab map. Regarding the remaining scene without a map ground truth, you can see the resulted map from both SegFloor and RTab map, where some elements are indicated. Through this scene, we want to highlight the cost of the point cloud optimization once a loop closure is detected. While our segmented point cloud is optimized in 37 seconds, for RTab map, the optimization of its dense point cloud costed almost 10 times more than our proposal. Here, you can watch a demo video of our application. This scene is regarding Hall 1, with a narrow passage. Besides the 2D OGM generation, you can also visualize the segmented point cloud. This other scene is regarding Hall 2, with an obstacle. Here, it is a more complex scene with various elements, varying from size and textures. Lastly, you can watch an extra scene recorded in an off-road environment. We conclude that the proposed technique actuates as an extension of the mapping stage of a feature-based visual SLAM, representing a link between the sparse point cloud and navigation activities. Tests made in both synthetic and real environment achieved a high accuracy map and good coverage. Besides, the method requires a low memory and low cost consumption, even for large scenes. Limitations consist of scenes in which navigable areas have no textures. Our main perspectives consist of IMU integration for a better camera pose estimation and extension of the binary map to a probabilistic context, a more suitable representation for merging maps generated by other sensors. Furthermore, to achieve even more computational optimization, integrating our technique in an embedded stereo vision system is a valid strategy that can also help with low energy consumption. Thanks for your attention and please check out our paper.
Thank you, Mirella, very much for your presentation. Very nice, very well done presentation, very didactic. Yes, Professor Luis Gonçalves is already saying on the chat that I myself is going to make several questions. It's yes, I have a few written down here. I'm very interested in the topic of Visual SLAM and occupancy grid generation. But well, as always, I'm going to ask first the audience if we have questions. No questions from the YouTube. From the audience, no questions too. Well, Mirella, I have a few, as I said. We could well talk all afternoon about your work. Is very impressive, very impressive.
Thank you.
Well, my first question is, well, you said yourself in the conclusion that is a limitation of your work, the fact that you're that it is based on features, right?
Yeah.
So it already answers one of my questions. What happens in featureless or textureless regions?
Yeah, basically this kind of limitation is a limitation of a visual SLAM based on features. So I add another limitation, which is features on the floor, because we need these features to apply the ray tracing. So yeah, we need it anyway.
It's a natural extension of visual SLAM. So you're going to have the same problems that those systems have as well.
Perfect. Yeah.
But what happens in between keyframe regions? So say your robot is mapping some region here, and then the visual SLAM triggers a keyframe, and then it takes longs to trigger another keyframe. So I believe you're gonna miss occupancy information from these regions in between keyframes. Am I correct?
Yeah, but this is something that you can adjust. You have several steps to define a keyframe. It's basically 5 in the open baseline. So you can adjust parameters, like, for example, I wanted to consider a scene that I wanted to add a new keyframe when the scene changed 5%. So I add a new keyframe. So in this case, I can be very conservative and add a lot of keyframes. Then I will ensure that this that you are considering will not happen.
Okay, so you hyperparameterize the visual SLAM system to trigger more keyframes. Is the solution you're mentioning?
This is the solution.
Okay, so as I said, we could be all night, well, all afternoon here, and I keep going asking questions. It's a very interesting topic for me. It's a very interesting work. So I find out one. Why did you choose to extend Open VSLAM instead of extending RTAB map?
Because RTAB map it uses the dense point cloud, and I use only the sparse point cloud, which is why we have again related memory consumption and time processing. So that's why I wanted to do another approach, which is using the sparse point cloud, not the dense point cloud. So yeah, that's why.
Okay. So do you have any other questions from the audience? No.
There's a question from Professor Becker in the chat.
Professor Becker,
Yes,
please go ahead.
I was going to tell that he asked it before me.
Oh, I missed it. Sorry, I didn't see it. Professor Becker, please, if you want to make the question yourself, please go ahead. Oh my God, I missed it completely.
No problem, Bruno, no problem. I'll try to be short because of the timing. Do you think, Mirella, that your algorithms can be used in an agricultural application?
Yes, I mean, if the occupancy grid map is something that it's important for this area, then yes, because I think as I showed in the video, we have the off-road scene that I tested, and it works pretty well in the off-road. So yes.
Yeah, it's because in the video we couldn't see if this off-road environment you had the presence of wind or plants, with leaves obstructing the way. So it's a little bit more complex. But anyway, I can send you a message later, making some questions. Thank you.
Thank you.
So thank you very much, Mirella, for your presentation. As Professor Becker said, he's going to text to send messages to you. I may send as well. So I have a lot of questions. I may get in touch with you later. Thank you very much for your presentation, Mirella.
And thank you for the interest in the work.
Okay. So now I'll call the final work in this session. It's on aquaculture enhancement through robotic behavior actuation by the work is by Federal University of Rio Grande. It's going to be presented by Bruna Guterres. Hi, Bruna. Do you wish to your video to be played by us?
Yes, could you play it for us, please?
Okay, sure.
Okay, thank you, Bruno.
Hi, my name is Letieri Avila, and I will present the work entitled On Aquaculture Enhancements Through Robotic Behavior Actuation. The presentation is organized into introduction, methodology, preliminary results, discussions, conclusion, acknowledgement, and reference. The present work approaches the Pacific white shrimp Lithopenaeus vanae and the proposed technologies for inference of its biomass. Due to the growth of shrimp farms and the reduction in natural fishing, the number of studies with these animals has been increasing in recent years. Technologies have been applied to the farms aiming at better conditions for the adequate development of the animals. To estimate the shrimp biomass generated, a system based on computer vision intends to acquire images of the animals considering their turbid aqueous environment and their preferential nocturnal habits. The purpose of a RBAS, Robotic Behavior Actuator System, is based on the magnetotaxis of shrimp with the objective of orienting them and reducing their activity, working as support for the computer vision system. Shrimp farming systems at high densities generate high levels of turbidity in the water. Bioflux-based technologies consist of transforming animal waste and leftover feed with added carbon into food proteins for the animals. This generate nitrogenous compound contributes to the non-renewal of water in the breeding system. Magnetobiology, which studies the relationship between the geomagnetic field and the orientation of animals, becomes a strong ally to computer vision systems by keeping shrimping paralyzed or with reduced movement. Previous studies confirmed this effect and stated that a magnetic field density of the order of the 160 microtesla is capable of reproducing said effect in shrimps. The RBAS design considers the use of a lighting system to have a double function to attract shrimp and assist in capture images. Therefore, an actuator system containing an image acquisition cache using computer vision techniques and a magnetostatic system should be responsible for obtaining a set for images capable of estimating the animal biomass after proper processing. Hence, this work raises a question: can the proposed RBIS increase the quality of the output of computer vision methods in aquaculture, such as biomass estimation? Furthermore, this work paves the way For the aquaculture, focused on technology that meets the growing demand for marine animals. The proposed actuator systems is shown in this figure. Lighting, behavior, performance, and excitation modules make up the RBAS. Green lighting helps the excitation modules and attracts through positive phototaxis the shrimp into the cage. The behavioral performance is generated through an artificial magnet system composed of neodymium magnets in a circular shape. The excitation module consists of a stereoscopic camera capable of capturing images in 3 dimensions. The cage has a cubic shape with hollow sides allowing shrimp circulation for image collection. The lighting module is designed with submersible green LEDs arranged on all sides except those used for animal circulation. The behavioral actuation module is built with a plastic support with neodymium magnets fixed according to the figure shown. The size and density of magnetic field generated by the assemble were tested and measured using a Tesla meter. The present configuration is capable of maintaining a uniform magnetic field on the order of 160 microtesla within the cage. In the figure, the sensor has installed between two disc-shaped neodymium magnets with dimensions 30 by 10 millimeters apart from 400 millimeters. The water used in this experiment came from a real bioflux systems in order to better reproduce the environment. The use of a circular shaped neodymium magnets, as shown above, replaces coils in the Helmholtz configuration, avoiding the circulation of electric current in the shrimp farming environment with high levels of salinity. In Figure A, the RBAS has the lighting module turned off and the shrimp circulate randomly in its vicinity. Note that behavioral actuation module is always active through circular supports with neodymium magnets. In Figure B, after activating the lighting module, the animals circulate more frequently inside the cage, having their natural movement dynamics reduced due to generate magnetic field. Thus, the best images are collected and properly stored for the computer vision system. As a result, there is a dispersion of animals with the lighting module switched off and the neodymium magnet supports removed. The collection of images is performed in real time, allowing the creation process to be monitored, being able to verify any anomalies during the breeding cycles. The Igley turbidity equals environment is not a problem, as the lighting and behavioral actuation model provide the ideal conditions for image collection. The RBAS becomes an excellent non-invasive tool considering that the animal biomass is measured without the need to remove the shrimp from the tank. In addition, issues such as shrimp depth and age can be solved with to the proposed lighting model. Other relevant environments such as fish farming codes use the same proposed tool for estimating biomass. For example, a mobile solution could receive RBAS to navigate environments with higher volumes of animals and data collection. Some similar works approach image collection systems with relative simplicity due to absence of relevant turbidity, one of the biggest challenges of the present work. The proposed solutions demonstrates great application potential, solving the problem of high turbidity. constituting an autonomous solution capable of supporting decisions in shrimp farming process. Real-time analysis of hearing systems converges to obtain more reliable data and biomass estimation with a high level of confidence. We would like to thank the financial support provided by European Union's Horizon 2020 Research and Innovation Programme. We would like to thank the Marine Aquaculture Station of the Federal University of Rio Grande for supporting laboratory experiments, as well as access to animals and farming systems. Here are presented the reference used in the work. Thank you.
Thank you very much, Letieri and Bruna, for your presentation.
Thank you, Bruna.
Now I ask if we have questions from the audience. No questions from YouTube. Do we have questions? Okay, Bruna, I have a question. Since your proposal is to use these magnets to, well, in a very simplified way, to control the shrimps, so they will stay in the determined region.
Yes, that's
in front of the camera, from which you can collect data from them and maybe, well, measure biomass. Is the main application, I believe, right?
Yes, yes. The main purpose of our work is to support image-based system for aquaculture applications on which we have shrimp or other animals. In our case of studies, the shrimp with bioflux systems on suspended particles and high turbidity that still complicates the use of this kind of system. So for now, we are on early development stage, on TRL level 2 to 3, and we are now going to perform some experiments on situ with animals and bioflux systems to support our idea and improve the technology readiness level.
So
I don't know if I understood your question.
No, it's exactly this. I want to know where in the life cycle of the project are you right now? Is that what you answered? And did you have any further results other than those from the paper? For example, did you already took pictures of collected images from the shrimps?
Yes, we have collected some new images, but we haven't used the magnetic field with animals yet. We just put the magnets on the water and inspected the magnetic field produced to check if the value would be appropriate or if we would have to modify our initial prototype. And now a new production cycle is about to start in the Brazilian INTA lab. And we now will perform more experiments to validate our proposal.
Okay. I believe one of my hypotheses would be if I was involved in this work it's a very simplistic hypothesis, but I would ask, can we in some way control the shrimps by regulating the magnetic field? It would be one of the first questions that I would ask if I was involved in the field, and then I would use the cameras to see if we are in fact controlling them, putting them in some determined regions of the image.
Yes, yeah, that's our idea to do it, but we based our research on some related works on the literature where other authors have inspected the behavior of shrimps under different magnetic fields, and they have concluded that the shrimps reduce their movement under certain magnetic fields and even freeze for a certain period of time, and it may support the aquaculture applications for image-based systems, since we can put the animals and assure they will be in front of the camera, but also when we need to remove the animals from the production ponds, for instance, because we can attract the animals for a certain region to facilitate the process. But we are working to see how it will work.
Okay, very interesting work for the shrimp farming industry, I believe. Julio is just saying in the commenting on the chat, remote controlled shrimp. Yes, it's magnetically controlled shrimp, I believe.
No, I was going to make a question, very fast one, if you have time, Bruno.
Yes, go ahead, Julio, please.
No, Bruno, very nice work. What would be the modifications to adapt to fish, for instance?
The first step would be to evaluate how fish respond to magnetic field. For instance, when we talk about shrimp, we know that depending on the development stage the shrimps they behave differently to magnetic field. Juvenile animals, they are attracted to the magnetic field, while younger animals, they are rejected, repulsed from this. So when we try to adapt our system to other animals, the first step would be evaluating how these animals react to such system, because we know almost all animals, they are regulated for magnetic fields, and for some of them we can use this kind of approach to modify and better address technology usage.
Okay, so we are already late in the session. Thank you very much, Bruno, for your presentation. So with this, we conclude session.
Welcome, Bruno. Thank you.
Thank you. We conclude session VSM 5, and now Professor Becker is going to chair the next session of LARS 2021. Thank you all for being with us. Professor Becker, please.
Thank you, Bruno. Thank you indeed. First of all, I would like to tell everyone that here in São Carlos, where I'm now, it's raining dogs and cats. So if something happens and you lose me, just I would like to ask Bruno or Julio to assume my place, okay? I had some problems just after lunch here, but now it's okay. Let's go. So I would like to welcome everyone for this section, aerial and aquatic vehicles number 4. The first presenter today will be Rafael Ferreira from Federal University of São Carlos. And the title of the paper is Sugarcane Line Angle Estimation based on pixel accumulation and Savitsky-Goulet filtering. Rafael, could you please?
Okay, good afternoon, everyone. Can you play the video, please? Hi, everyone. I am Rafael Ferreira, and I'm going to present the paper Sugarcane Crop Hole Orientation based on Pixel Accumulation and Savitsky-Goulet Filtering. I am with the advisor, Professor André Carmona, together with the Federal University of São Carlos. So, sugarcane is one of the main crops in the world. Brazil is the largest sugarcane producer, followed by India, which together account for 59% of the total produce in the world. Together, therefore, any innovation in this area represents a lot in the trade balance, as well as in the preservation of the resources and the market supply. There were several technological advances to achieve these numbers, but we are interested in mechanization and automation of harvesting. Currently, These sugarcane operations are almost 100 mechanized. When the harvest enters in the cane, care must be taken so that the wheel does not pass over the plant, causing crushing. The automated harvesting process is carried out following the georeferenced lines recorded in a GPS system embedded in the combine. GPS signal position error can vary from 9 meters to 2 or 3 centimeters. Therefore, in agricultural applications, the GNSS RTK correction system is needed to provide geographic accuracy. The RTK base is a null position and sends the GPS signal error to the combine. The combine receives the GPS coordinates and applies the offset. The RTK base can be up to 60 kilometers away from the combine, and the signal is transmitted by radio frequency waves. But what happens if the RTK correction signal is lost? In these situations, the automatic pilot of the agricultural machine loses the precision of the harvest line, causing the bells to pass over the crop or collide with the other tractors. So how can we solve this problem? We seek to use local processing, using a real image to identify the crop line angle. This rotation can be measured and compared with the combine orientation. The algorithm can be used as a real-time method to transmit the guidance of the crop lines to the combine. Our algorithm is composed by 2 big steps, and it's based on analysis of vertical projection of the image obtained by rotating 108 degrees. After that, we apply a filter to identify the maximum variation. Looking with more detail about image segmentation process, the aim of this process is to classify the image in 2 regions, the soil and the sugarcane. First, we need the original image input on the algorithm and apply the first filter, the vegetation index, namely excess green, in order to classify between green plants and the background. After that, double thresholding is needed. Binarization by odd-sum thresholding performs better adapting to highly changeable environmental conditions. Here, we have the image of the excess green index and the odd-sum thresholding. After all, we need apply extra morphological dilations to expand the segmentation plans. So this image is the output of the first big process. The second process is the orientation detection, composed by pixel accumulation and Savitz-Golay filtering. On the image, white pixels is equal to 1 and represents the sugarcane. Black pixels is equal to 0 and represents the soil. So we get the array of sum of the vertical projection represented by blue line. After that, we apply the filter used to identify the rate of change regardless of the magnitude of the accumulated value represented by the orange line. So we have to apply this process in an image in all orientation by a specific angle step. With the full sweep of all angles, the orientation of the cut lines will be at the maximum point of variance vector. In this image, the maximum is 19. The red line drawn by the algorithm confirms the result. Here, some of the results from our dataset show good orientation accuracy, but some images with dense sugarcane do not generate large variations and error increase, like this. Here is the main analysis of the entire dataset. We made experimental tests varying the rotation resolution and the window size of the filter. In red is the best result of the trials. We have the best result for 1 degree over rotation resolution, 15 window size pixels. We got 0.9 error median degrees and 1.5 interquartile degrees. In a specific time processing of 0.875 seconds. In the graph on the side, we can observe the amplitude and the occurrence of outliers in relation to the absolute errors. The results show that the proposed methodology was able to detect the curve orientation angle with a median absolute error of 0.9 degrees in a interquartile of 1.5 degrees. What about speed? With this time processing, we can use this method as a real-time process. About outliers occurs when low variation between plant and soil. We have challenge too. In night operations, we have to apply extra illumination and high dense sugarcane, where low variation between plant and soil is present. Other advantage of our methodology is use of monocular camera, local processing, and robust and presence of gaps. This is our references, and I would like to say thanks for watching, and please let me know if you have some questions. Many thanks.
Thank you, Rafael, indeed. Very nice presentation. So I would like to hear from the audience if we have a question. No questions here. Okay, I have a question for you, Rafael. When we are doing some experiments in agricultural environment, it's always hard to have a good definition of the ground truth. How did you do that in your experiments?
Well, the ground truth orientations of the curve hole were determined by a manual method based on overlapping bars draws manually with a known angle, basically.
Okay, but can you figure out another way to do it? You know, maybe adding something in the environment that you can use, like a beacon, or I don't know.
Another method to evaluate the ground truth, is it?
Mm-hmm. Yep.
Well, it's hard to think about that, because there's a lot of rows that is not in the same angle. So when you think in an automatic process of drawing the ground truth, it's really hard to do. We were thinking about it to make this process more fast, because a lot of my time spent is drawing the ground truth.
Yeah, that's why I was thinking about a way that you can maybe search some little change in the environment that you can use as a good information, so you don't need to do it everything by hand. But we can talk about this later. Very nice work. Thank you. Congratulations.
Okay, thanks.
So if you don't have any more questions, I will go for the next presenter. Let me check here. It's Igor Maurel from, let me check, the Federal University of Rio Grande do Sul, maybe. Geometric primitive fitting in large structured 3D points clouds acquired by drones. Are you here, Igor? Igor, I think your microphone is, yeah.
Hello?
Not yet. Yes, now we have you. Good, Igor.
Hello, Marcelo.
Good. Thank you for being here. And should we play your presentation, or you're going to do it by yourself?
Yes, please. Play the presentation.
Okay, so I ask you. Good, it's there.
Hi, everyone. My name is Igor Pardo Maurel, and my work is geometric primitive fitting in large structured 3D point clouds acquired by drones. The authors of the work is me, the Professor Paulo, Professor Carlos, and Cauê. Firstly, introduction, we are talking about point clouds that are normally acquired by 3D scanner using LiDAR systems or multi-view camera systems. And we are talking about large structures. We are talking about civil constructions and industrial plants. In the task of geometric primitive fitting, few methods focused on large structures. Science, there is a lack of large structures data with ground truth to geometric primitive fitting. So a problem definition, given a set of endpoints with optionally their associated normals, that is the point cloud, the algorithm must generate a set of k primitives defined by a type and the parameters. That is a fitting problem, which each one has a set of points representing it in the point cloud, input point cloud. That is a segmentation problem. We have to solve them both together. So the primitive types normally used, they are plane, sphere, cylinder, and cone. So the objective of the paper is to evaluate the state-of-the-art methods in the geometric primitive fitting in point clouds of large structures and propose a full pipeline to fit the geometric primitives based on this. So for this, we need to evaluate the state-of-the-art in processing point clouds of large structures and in geometric primitive fitting. Propose a pipeline to do geometric primitive fitting in point clouds of large structures, and do a parameter tuning in the existing methods to better solve the problem. So the related work, firstly in the context of large structures, we have many works to work with point clouds in large structures. Many of them talks about geometric primitive fitting as an important step to do 3D data simplification and CAD reverse engineering. Some works talks about filters as downsampling filter, outlier removal, and point cloud division, and the other works talks about the problem of memory consumption. Newer works solve some tasks as semantic segmentation using deep learning techniques as Randall-Net and SPG, but for geometric primitive fitting, there is no deep learning technique that solves it for point clouds of large structures. In the geometric primitive fitting works, we have efficient Transac, SPFN, and ParseNet as the three bigger methods. Efficient Transac has a stochastic foundation, fits planes, spheres, cylinders, cones, and torus, and receives points and normals as input. SPFN and ParseNet are newer methods that has deep learning as a technical and theoretical foundation. They fit the same primitives almost, but they are focused on small structures and not large structures, as efficient Transac is focused on any structure. The methodology, firstly, we talked about the pre-processing. We have three steps that are filtering, normal estimation, and normalization. In filtering, we have crop box, downsampling filter, and outlier removal. In normal estimation, we have a technique to estimate normals in the point clouds that doesn't have it. Since efficient Transac needs the normals, and the ParseNet too. And normalization is needed for both methods, SPFN and ParseNet. The steps are rescale, noise addition, centralization, canonical alignment, and cube-based rescale. In the processing, we have the three fitting methods. The first is efficient ransack, has an available implementation on Seagull, configured to fit plane, sphere, cylinder, and cone. Using the default parameters and the tuned versions. Efficient ransack has 5 parameters. Probability, that are the probability to lose the bigger primitive, the stop condition of the method. Mean points, that is the minimum number of points to a sample be considered a possible primitive. Epsilon, that is the maximum distance between a point and a primitive to this point belong to that primitive. And the cluster epsilon, that is the maximum distance between 2 points to then be considered neighbors. And normal threshold, that is the same thing that epsilon, but for normals instead of distance. SPFN and ParseNet both have available implementations on GitHub. We trained an SPFN to small structures, the same data as the paper of SPFN, and ParseNet has available the trained weights for small structures too. So the results in the first experiment, we want to know if which geometric primitive fitting method is better for large structures. So we want to answer 2 questions. Which method is better in geometric primitive fitting of large structures? And the second is, the deep learning methods used for small scale clouds are capable to deal with large scale point clouds? The procedure is sample a point cloud with 10K and the other with 1 million points in a mesh, test 3 methods in these clouds, and compare the results using the knowledge about the mesh model. So here's the data, the mesh model, 10K points sampled above, and 1 million here. The results for 10K is that efficient ransack segments well the great planes of the structure, and SPFN and ParseNet do a random without geometric value segmentation. With 1 million points, efficient ransack segments well better, way better the primitives. Each primitive has a color, and SPFN and ParseNet has a high memory cost to process this, and is not possible to process. The conclusion about the experiment, even in taken points, that is the context of number of points of SPFN and ParseNet, efficient ransack is better than them. Training a data set of SPFN and the training sets of SPFN and ParseNet, they has 10K points normally, but the characteristics of the models is different. A characteristics of a small structure model is different to the characteristics of a large structure model. The memory consumption is very high with the increase in the number of points for SPFN and ParseNet, and we need models, learnable models, to do it for large structures. But we need first the data with ground truth. In the second experiment, we evaluate the proposed pipeline in a drone captured point cloud. The questions are, how well the full pipeline goes in large scale point clouds, how the fitting of efficient ransack can be improved. In the procedure to answer these questions is apply pre-processing a drone captured point cloud, adjust the parameters of efficient ransack using some assumptions, and compare the 2 versions of efficient ransack, default and adapted. So the data is a point cloud made by Pix4G using several drone captured images. That point cloud has 22 million points with position and color. The pre-processing in filtering step was used just the downsampling to a resolution of 2 centimeters, and output has 408K points. Normal estimation was done with a 5 cm radius sphere, and normalization, just centralization and alignment was used. So the 2 definitions, the default definition of Seagull has mean points, epsilon, and cluster epsilon as adaptative parameters, mean points with the number of points, and epsilon with the size of the bounding box. And our definition R1 has fixed parameters. The assumptions to define the fixed parameters are, the first is the small details of large structures. If you base your mean points in with base the number of points, you must lost the small details of a great scale point cloud. The reduction of computational cost. If you increase the probability, the computational cost will decrease. If you decrease the probability, the computational cost will increase a lot. If you want a low processing time, you must increase the probability. But if you increase the probability, the results will be bad. 3, the restrictions imposed by downsampling filter to cluster epsilon. Cluster epsilon must be the lower resolution satisfied everywhere in data. But if you apply the downsampling filter, you change the resolution of the point cloud. So you need to use the resolution used in downsampling filter to define the cluster epsilon. And 4, the primitives don't always pass over point. In the Segal definition, cluster epsilon and epsilon are equal, but not ever the primitives pass above the point. So the epsilon must be a little bit higher than the cluster epsilon. So the results in R1, we found more primitives than R2 with a higher peak coverage and a little bit higher time of processing. The results of the flow, the 2 cylinders of the center are segmented as 1 cylinder, but the segmentation of the ground plane is good. In the R1 configuration, we have the 2 cylinders almost segmented as 2 cylinders with some mistakes and some other segmentations that are good to know in the background and in the ground. So conclusions about the experiment. The preprocessing all of the execution with a good parameters in a low time. The efficient run-stack can be improved looking to the presented assumptions. With a low mean point, the computational cost will increase. So you need to increase the probability too. The epsilon must be a little bit higher than the cluster epsilon. And if the point is over segmenting, you have to decrease the probability or increase the epsilon. So the conclusions, the efficient run-stack well fits geometric primitives to point clouds, but it can be improved with a preprocessing and parameter adjusting steps. The deep learning based approaches are not ready to solve this problem for large structured point clouds. So thanks. Any questions, you can answer me. You can question me.
Okay, Igor, thank you very much for your presentation. It's a very interesting work. And I would like to hear from the audience if there is a question. No questions from YouTube. Maybe while the audience is planning to make a question, I can make a question for you. As you are planning to use your approach to inspect severe structures like, say, bridges or transmission towers, things like this, I do believe that you can add in this environment something like beacons that you can use to improve your ground truth and maybe to have better results. If you can do that, I think it's a very nice way to solve this problem. And are you planning to deal with all the information maybe the drone or post-process it after the experiments?
We are planning to use the technique, the GPR technique, to do automatic as-built of industrial structures. The focus of the research is in industrial structures, and the focus is not interfering the structures, so not use any recon or landmark that we know in the structure to help in the generation of the results. I think that's it.
This works well in applications when you are really doing the inspection. But if you want to publish a paper, you need this.
Yeah, okay.
To guarantee that your approach is really good. That's something that the reviewers will ask you.
Normally
But
the ground truth data are simulated with CAD models, and you sample point clouds and do a ground truth directly matching the CAD with the point cloud.
Okay. But the question was that are you planning to deal with all the data inside the drone, process everything with the drone, or just get the data and after the experiments take to a better computer and process everything?
To take the data and process everything. To take the point cloud and process. If the drone uses cameras or LiDAR, don't matter for us. We just take the point cloud and process to do the geometric primitive fitting.
Okay. So no more questions. Thank you indeed, Igor.
Thank you
for your presentation. Let's go for the last presentation of this afternoon. Is detection of invasive vegetation through UAV and deep learning. And the presenter is Charles Camargo from Federal University of São Carlos. Are you here, Charles?
Yes. Hello, everybody. Hello, Marcelo. Good afternoon.
Hello. Good afternoon. Should we play your presentation, or are you going to do it by yourself?
Please play the presentation.
Okay, Julio, please.
Hello. I show you the detection of invasive vegetation through UAV and deep learning. This work was made by me, Charles Camargo, Pedro Kim, Aline Almeida, Lídia Rocha, and Kelly Vivaldini in Federal University of São Carlos. I will show you the following topics. Introduction. This presentation begins by introducing the problem that motivated the development of this work. Methodology. The framework used in this work starts with data collection and pre-processing images, the choosing classifier, techniques used, and creation of custom laws to improve our results. And finally, the results and discussion that can guide future works. Maintaining biodiversity is very important for the integrity of the ecosystem. However, exotic species to the local environment can be introduced innocently, as in ornamental plants. These exotic species can have a competitive advantage and dominance over local species. And when they overcome the barrier of the colonization, reproduction.
Professor, I will change to YouTube video since this one seems like a bit corrupted. Just a second. I have checked on YouTube, it's okay there.
Okay, no problem. We wait.
Pre-processing images, the choosing classifier, techniques used, and creation of custom laws to improve our results. And finally, the results and discussion that can guide future works. Maintaining biodiversity is very important for the integrity of the ecosystem. However, exotic species to the local environment can be introduced innocently, as in ornamental plants. These exotic species can have a competitive advantage and dominance over local species. And when they overcome the barrier of the colonization, reproduction, and dispersion, they become biological invaders, which has caused great concern. Several problems such extinction of native species, irreversible changes in the ecosystem, negative impacts on the biodiversity and ecological process is possible. The biological invasion is the second biggest cause of biodiversity loss on the planet. Some studies point this situation. A study in Brazilian conservation units identified several exotic species installed. The Hydrogen coronario is one of the biologically invasive vegetation found, invading extensive areas of native forest and causing many impacts. Large concentration of Hydrogen coronario can serve as a habitat and even food for capybaras. It may result in the proliferation of ticks that carry human diseases. About 20% to 50% of all Brazilian biodiversity is in the Cerrado, and many of these areas are difficult to access or with large territorial extension. Covering more extensive areas in less time adds a big value to monitoring. Beyond that, accessing hard to reach regions remotely is also an advantage. So the automatically and accurately identify vegetation in large areas favors monitoring work at all. Since exotic species can become invasive and pose a risk, is essential to monitor them. However, native forests can be difficult to access and have high human and financial costs to monitor and to execute this job. Remote monitoring and automatic identification can represent significant gains, and the use of semi-orbital sensors such as UAV has a much lower cost than satellites for the same purpose. To perform this work, we elaborate on the following framework. We divide into two major areas. Firstly, data gathering, and then the detection of invasive vegetation. To collect data remotely, we use the UAVs to fly over the area and take pictures. If the image collected, we did the processing and separated them into training, validation, and test database. Finally, we carry out to the classification. We made 3 flights with the UAV DJI Phantom 2 equipped with GPS and a camera. We performed all flights at 40 meters above the ground, and by associating the image with the GPS coordinates, we were able to create our orthomosaic. In the figure ground truth, we can see a single captured image, the mask created, that is the ground truth, and finally, this same mask being applied as a filter over the image. In the orthomosaic figure, we can see more than 400 linked images forming two orthomosaics, two different orthomosaics. The orthomosaic A are images collected at Fazari Dam, and the orthomosaic B are images collected at the Orto Municipal. Among the new solutions found in the literature, the use of deep learning algorithms has been highlighted by the results, and the convolutional neural network today presents excellent results in computer vision problems. The UNet algorithm, created and widely used in biomedicine, has the advantage of working with a small mass of data, according to its creator. The UNet network has this name because it can be represented in a graphic in the form of the letter U when contracting, downsampling, and expanding, upsampling. We carry out several pieces of training, changing between classifier and loss function. We also use different learn rates and data augmentation settings. However, the algorithm had a great difficulty on the edges between invasive vegetation and other vegetation types. We decided to increase the error penalty at the edges, replace the standard binary cross entropy with a custom loss function. The function that calculates the error loss finds the distance between the center of the positive class, Hitch coronarium, and its limits, creating an inverse Euclidean distance transform. The custom loss function multiplies the mean squared error by the Euclidean distance transform to create this scenario. In the first figure, it is possible to see how the AUC hit 89%. It took 70 epochs. With standard binary cross entropy, the loss had hit at 25% as its best result. After changing to custom loss, the loss dropped to 12% in training and validation, as seen in the figure. We trained the unit in various conditions. With a dataset from different seasons of the year, we made all the flights in a small distance of the soil and sunny days. So we did not feel any impact of the clouds in our result. We believe cloudy days or intense change in brightness can impact the outcome. Since the proposal of this study was to work with RGB images, we do not use spectral images. Future works may mix these approaches. In other words, the two kinds of photos beyond the cloudy days. After a few epochs of training, even if a small data set, some points could be verified. The data augmentation is an essential tool to improve generalization, but more significant oscillations in the zoom can negatively influence the results. They use the
Okay, thank you, Charles, for the presentation. It's very interesting. We see that it's a very actual problem in Brazil and everywhere in the world. It is invasive species. It's very hard to deal with them. So it's very important to detect and try to eliminate them. Good. I don't see any questions from YouTube, but I have some questions for you. Did you try to fly your drone in different altitudes, trying to check if you can improve your results getting closer to the vegetation?
No, in the fact, we use the same route and the same altitude all the flights.
Okay, and do you think that if you change the sensor, starting to use some more sophisticated optic sensor, maybe to detect reflectance, something different, you could solve these problems you are facing?
And yes, I think the reflection can improve the results, but this work we want to work with RGB images for our study, but increase other approaches can result in better results.
Yeah, okay. So maybe it's a nice move in the future to think about making a partnership with the Physics Institute in your university, Federal University of São Carlos, or even at USP. You can run some experiments trying to detect the right frequencies, and then you can use cheap cameras with a filter and get just that, that frequency of light to detect the invasive species. Maybe it's just an idea. Maybe it's a nice move in the future. Okay. So the audience, do you have some questions? Luis, Bruno? No questions. Okay. So Charles, thank you indeed. It's a great job. You did a great job, I see. And I hope to see you soon. We arrived to the end of the section, aerial and aquatic vehicles 4. And now I switch to Bruno. Thank you indeed. Bye-bye.
Thanks, Professor Becker. I will just flash screen so while Bruno makes the announcements.
So thank you, Professor Becker, for chairing the last session of LARS. That was the last technical session of LARS. Thank you, everyone that presented their works here on our symposium. Julio, I believe now, according to our schedule, you're going to present the results of the contest in dissertation and thesis in robotics. Am I correct?
Yeah. I don't know if the audit, or if
Chun. Isn't it?
Yeah, I was looking for Professor Perico. If he was, he told me that he was trying to be present today, but maybe he's just too busy with the classes. I can carry on alone. I will share my screen. I made a very short presentation. It won't take long. I know that Professor Luis has some informations also to share with everyone. So I will be very brief.
It's on you, Julio.
Yeah,
I just want to say for everyone, if all of you are invited to be in the SAR meeting that will happen at 7 p.m. That's it. Nothing more than that. It's on you and Bruno now. Thank you very much, all of you, for being here, and we invite you for LARS 2022. Go ahead.
Yeah, thanks, Professor. I made a very short presentation. I know that Professor Anderson Abner last year was very, very brief. I will try to be as brief as him. So I will just start. I will do it in Portuguese, respecting the presentations and the flow that we followed on the contest. But I really would like to suggest to the chairs to the next year, maybe we can keep the presentations in Portuguese or English, but make all the slides in English. It would be helpful to the international guests, maybe. Next year, we can try it. Então, eu vou falar em português, tá, pessoal? É só para a gente manter o mesmo padrão que a gente fez no concurso. Então, uma apresentação rápida sobre como é que foi a metodologia da avaliação que a gente usou esse ano, tá? Foi uma das demandas que o professor Luiz me pediu quando ele me convidou para ser chair, era que a gente deixasse bem transparente. Eu vou tentar seguir isso bem à risca. Então, a gente recebeu os trabalhos dos candidatos, era um artigo de até 12 páginas, né, que a gente entende que é realmente pequeno e tal, e por isso a gente também recebeu as teses e dissertações completas dos alunos, dos candidatos. No entanto, para a gente evitar fazer muito trabalho de leitura de tese de dissertação, até porque a gente tem uma quantidade limitada de recursos humanos, eu fiz uma primeira, eu e o professor Périco, a gente decidiu fazer uma primeira rodada de eliminação, não considerando trabalhos que recebessem reject ou strong reject, ou weak reject, em alguma das pontuações, né? Não foram muitos, mas isso aí facilita para a gente mais na frente, porque a gente quer ser o mais justo possível. No início, nas avaliações do GEMS, eram 3 professores, a gente felizmente conseguiu colocar de forma que nenhum professor avaliasse um trabalho de sua própria instituição, e aí, assim, infelizmente a gente não tem como saber quem é colega de quem, né? Mas a gente fez questão de manter esse tipo de critério na hora de fazer a avaliação. O que quer dizer que vocês precisavam ter um bom trabalho escrito no formato de artigo. Isso aí fazia diferença para o CTDR, não só a tese de vocês. E aí depois, com esses trabalhos, depois dessa primeira rodada de eliminação, a gente fez a avaliação do texto inteiro. E da mesma forma, a avaliação do texto inteiro foi feita por mais 3 professores, não obrigatoriamente os mesmos que analisaram o artigo, embora eu tentei manter na medida do possível, nem todos puderam, então a gente acabou fazendo a seleção, mas ainda assim eu consegui manter o critério de que nenhum professor ia avaliar uma dissertação que tivesse da mesma instituição, e ao mesmo tempo eu garanti que nenhum professor que estivesse participando do campeonato, da competição, avaliasse um trabalho que está na mesma classificação, na mesma categoria dele. Então, um professor que tem trabalhos em doutorado não vai avaliar trabalhos de doutorado, ele só vai avaliar de mestrado, e vice-versa. Tá? E aí, por fim, a gente teve as apresentações também tiveram 3 avaliadores, e aí a gente teve o resultado final. Tá? Óbvio que trabalhos que não foram apresentados, eles não vão entrar nessa avaliação. A gente teve, no total, 9 trabalhos de mestrado submetidos, né, e 2 deles foram removidos nessa etapa inicial, e depois tivemos 2 trabalhos de doutorado, como eu falei no início, 2 a menos do que no ano passado. A gente teve mais mestrados do que no ano passado, e em compensação tivemos menos doutorados. Assim, a gente pode imaginar que seja já um impacto um pouco da pandemia, né? Os trabalhos de robótica são bem práticos e a pandemia dificulta um pouco. E aí, assim, a gente teve um total de 9 trabalhos aí avaliados depois por 15 revisores, e aí a gente conseguiu dividir aí os revisores para tentar ser humanamente possível, né, para todos eles, e aí aquelas restrições que eu falei para vocês. Então, vamos para o que todo mundo está esperando, né, que são as classificações dos trabalhos de cada um dos trabalhos. Cada um dos trabalhos vão ser classificados entre... Eu vou apresentar o terceiro, o primeiro e o segundo, né, que são os que recebem o certificado, e depois eu apresento toda a classificação. Tá? Então, eu vou começar pelo terceiro melhor trabalho, como de praxe, né? Todo mundo começa sempre pela parte mais... Quem está um pouquinho mais embaixo para dar um pouquinho mais de expectativa. Tá? Então, o terceiro melhor trabalho foi o Learning Push Recovery Strategies for Bipedal Walking. Foi um trabalho ótimo que a gente viu que é possível utilizar a inteligência artificial para fazer aprendizado de equilíbrio, e ao mesmo tempo, assim, a apresentação foi hoje pela manhã, e foi realmente bem interessante ver que era possível usando AI, inclusive fazer cascata de controladores, né? O aluno apresentou, o Dixiano apresentou que ele usa no futebol de robôs, e aí assim, a gente achou bem interessante o trabalho. Ele inclusive está presente, eu acho, ele estava esperando aí. Mas foi realmente um trabalho ótimo, tá? Foi bem difícil, na verdade, avaliar. Os trabalhos de mestrado foram todos ótimos. Vamos para o próximo trabalho. O segundo melhor trabalho de mestrado foi a Arena, a plataforma para experimentação de sistemas multirobôs em ambientes industriais. Também foi apresentado hoje. É um trabalho que mistura, inclusive, a gente que estava assistindo, a gente ficou na dúvida, né? Qual era a parte real e qual era a parte virtual. Eu acho que esse era justamente o ponto específico do trabalho. O trabalho faz questão de misturar real com virtual para que seja possível e mais escalável fazer projeto de plantas robóticas, de plantas automatizadas através de robôs, né? Então você pode ter tanto robôs virtuais quanto reais interagindo entre si, payloads reais e virtuais interagindo entre si, construções reais e virtuais interagindo com os robôs, o que realmente foi um trabalho bem interessante e bem legal. E aí, por fim, né, o melhor trabalho de mestrado do concurso de tese de dissertações desse ano foi Interaction Models Between Humans and Lower Limbs Exoskeletons Applied to Robotics Neurorehabilitation. o professor Danilo chegou. Esse trabalho foi realmente assim, a gente estava comentando que ele encaixa muito bem com alguns trabalhos que a gente viu em todo o LARS, porque ele é um trabalho de reabilitação robótica, né? Embora assim a gente viu que o trabalho ele em si não é um trabalho de reabilitação, ele é um trabalho de modelo e simulação da possibilidade de você controlar um membro prostético robótico e aí ao mesmo tempo usando um modelo simulado, né? Assim, o grande problema resolvido por esse paper, por esse trabalho no geral e que foi claramente mostrado nas publicações é que não existe ainda um modelo fechado que permita o pessoal que desenvolve exoesqueletos, que desenvolve robôs de reabilitação, fazerem a modelagem inicial e os testes iniciais de forma satisfatória, antes de colocar na pessoa ou no paciente, para poder fazer os testes reais da prótese ou do exoesqueleto. É o que foi mostrado com bastante critério pelo Denis, né? E aí a gente conversou bastante lá durante a apresentação, foi uma apresentação ótima, inclusive. Parabéns, Denis. O primeiro lugar do concurso de teste de dissertações, né, recebe um convite, e aí o professor Luiz Marcos está aqui para convidar, né, para a publicação no DINT. Então, você com certeza vai ter mais e ainda publicações. Que foi uma das coisas que a gente mais comentou, assim, os trabalhos de mestrado tiveram um nível muito alto mesmo. E aí, esse nível alto dos trabalhos de... esse nível alto dos trabalhos de mestrado, a gente chegou a colocar no site, Luiz. Então, a gente não foi surpresa, não. A gente colocou no site que os primeiros lugares iam ser convidados.
Just kidding.
Pode ser surpresa se você der para o segundo e terceiro também. Aí a gente fica satisfeito, porque realmente os trabalhos eram muito bons, certo? Então, ainda assim, certo, pessoal? Para que a gente não fique... Para vocês entenderem aí, depois que a gente calculou aquelas médias, vocês podem ver que alguns trabalhos ficaram bem próximos uns dos outros, o que foi decidido basicamente pela qualidade do primeiro artigo submetido ou pela apresentação que foi feita nos 2 dias do CTDR, né? Então, foi realmente muito legal ver trabalhos de mestrado com um nível tão alto. Assim, eu realmente fiquei impressionado quando eu estava lendo alguns dos artigos que eu fiz a revisão, que ficou o nível do artigo, né? Eu até falei com o professor Bruno sobre isso. Então, assim, esses aqui foram os trabalhos de mestrado, tá, pessoal? A gente vai passar agora para os trabalhos de doutorado. Professor Périco, se você quiser falar alguma coisa, você pode me interromper, fica à vontade, tá?
Tá bom, então... Júlio, obrigado aí. Pode continuar, no final eu falo, pode deixar.
Tá ótimo, tá ótimo, tá ótimo. O professor Périco junto com, foi o chair, o co-chair, né, ou o chair também, né, do evento junto comigo, né, os 2 chairs, na verdade. Assim a gente resolve os pepinos, basicamente. Então, os trabalhos de doutorado, como eu falei para vocês, né, a gente teve apenas 2 nesse ano. A gente com certeza vai ter mais no ano que vem, né, pelo nível dos trabalhos de mestrado que a gente recebeu. A gente imagina que devam vir bons trabalhos de doutorado nos próximos anos, pelo menos. E aí, desses 2 trabalhos de mestrado, claramente um vai ficar primeiro e outro vai ficar em segundo. Então, eu vou começar apresentando o segundo trabalho melhor, de acordo com as avaliações. Mobile Robots, a Study on Sensing and Perception Systems. A gente viu a apresentação desse trabalho hoje, os trabalhos de doutorado foram apresentados todos hoje, né? Os de mestrado foram metade. E a gente chegou à conclusão que o apresentador tinha construído 2 ou 3 teses, né? Porque ele usou um formato de tese inovador para a universidade dele, para o TFPR. Ele usou uma coletânea de artigos, né? Que ele conseguiu publicar bastante. E aí, construindo a coletânea de artigos, ele conseguiu a tese dele de doutorado. E aí, assim, o artigo dele apresenta nesse sentido, a apresentação dele, inclusive, foi nesse sentido, onde ele começa mostrando o primeiro trabalho que foi usado no doutorado, depois o segundo, depois o terceiro, depois o quarto trabalhos, todos eles publicados em periódicos com bastante impacto e com trabalhos realmente com bastante corpo, com resultados, e isso durante os 4 anos de doutorado, né? E por fim, né, o segundo melhor trabalho, que vocês já devem saber, o pessoal que está aí, né? o primeiro melhor trabalho, no segundo, agora o primeiro, né? Não é o segundo mais, tá? Desculpa aí. Então, planejamento de caminhos seguros e suaves, baseado em espuma probabilística para sistemas robóticos autônomos. Também foi apresentado hoje mais cedo, trabalho do professor Pablo Alsina, aqui da UFRN, certo? Eu não revisei, como eu sou da UFRN, esse trabalho, claro. E, assim, esse trabalho, da mesma forma como o trabalho anterior, tem uma quantidade impressionante de publicações, o aluno apresentou, e todos os revisores avaliaram muito bem a qualidade da publicação do autor. Foi realmente assim, uma quantidade muito expressiva de publicações, ambos têm uma contribuição científica muito relevante. Tá? Então, a gente, com certeza, foi difícil avaliar esses trabalhos que a gente recebeu esse ano, por toda essa bagagem que eles vieram aí. Então, com certeza, todos eles estão, assim, a gente infelizmente tem que dizer quem é o primeiro, quem é o segundo, mas nada impede aí do pessoal da robótica fazer aí convite de todo mundo para publicar no JINT, tá? Porque realmente a qualidade é muito boa de todos os artigos que passaram aqui no concurso, tá? Muito obrigado, pessoal, por terem confiado na gente para fazer as avaliações, por terem confiado no concurso, e aí vocês podem ficar à vontade. Eu vou chamar o professor Danilo para ele falar alguma coisa, se ele tiver, né, gostaria de falar alguma coisa, né? As avaliações também estão aqui, eu vou colocar elas no site, logo depois, talvez amanhã. E é isso, muito obrigado a todos, obrigado por participarem no LARS, obrigado aos competidores do CTDR desse ano.
Legal aí, pessoal, né? Como o professor Júlio já comentou, aí o nível dos trabalhos foi muito bom, né? Os trabalhos de mestrado ali sensacionais, os trabalhos de doutorado com muitas e muitas publicações, né? O que era bem interessante ali mesmo, né? Foi algo que chamou bastante a nossa atenção, né? A quantidade de publicação dos trabalhos de doutorado e até dos trabalhos de mestrado em alguns casos, né? Então, a avaliação é difícil, né? Vocês podem ver aí mesmo, o professor Júlio colocou as notas ali, vocês podem ver que elas são próximas, né? São muito próximas todas. Então, o nível dos trabalhos é muito bom, né? O que é bem legal para a gente, no fim das contas, né? A gente acaba aí tendo contato com muitos trabalhos que são legais e para a gente também acaba sendo um prazer aí fazer essa revisão e ajudar aí na organização. Eu também agradeço todo mundo aí que ajudou, foi bem bacana, espero continuar tendo aí trabalho nesses níveis, vai ser legal. Obrigado.
Valeu,
aí,
pessoal. Muito obrigado,
Até.
muito obrigado também, assim como o Danilo falou, né? Obrigado ao pessoal que gastou energia fazendo as avaliações, tá? Assim, a gente puxa a orelha, né? Mas vocês conseguiram, a gente conseguiu. No final, assim, eu tava realmente com muito medo de mim e o professor Danilo, a gente precisar ler todas as teses e dar as notas, né? Mas no final, a gente viu que o comitê técnico trabalhou e conseguiu avaliar todos. A gente recebeu praticamente, assim, a gente teve, na parte de leitura da tese inteira, eu e o professor Danilo, a gente praticamente não teve tanto trabalho, assim, pelo menos não quanto a gente esperava que ia ter, o que foi ótimo. A gente pôde contar, pôde confiar com vocês, pôde confiar em vocês, né, do comitê técnico. Muito obrigado mais uma vez. Tá? E obrigado aos participantes. A professora Roseli está tentando conectar aí, que também participou do nosso comitê técnico. Ver se ela consegue conectar. Mas, bem, pessoal, é isso. Eu vou convidar todos vocês para a reunião logo mais tarde, que o professor Luiz Marcos acabou de anunciar, né, às 7 horas, para a gente decidir o futuro, especialmente do evento, né? Mas o professor Bruno está aí também, como o chair, os professores Paulo Drews, Eduardo Todd, Marcelo, todos vocês foram bastante relevantes aí para todo o evento. Muito obrigado.
Quer falar alguma coisa, Bruno?
Não, Luiz, pode falar.
Para a gente encerrar o
eu posso falar,
né?
pode falar e depois a gente faz o encerramento oficial, né?
Certo. Assim,
Está faltando Carla, né, Luiz? Está faltando Carla ainda, né? Eu não sei se ela está encerrando lá no WRE.
Não, ela já encerrou, mas ela vai estar mais tarde na reunião. Acho que ela está com as crianças. A Carla tem 2 menininhos pequenininhos, né? Então ela tem que... Assim como você tem também, né, Júlio? 2 ou 3 aí, bebezinhos?
2.
São 2. Tá aí do lado, né? Não. Então, Assim, eu não tenho palavras aqui para agradecer, né, a todo mundo que está aqui agora e todo mundo que colaborou para que a gente mais uma vez conseguisse aí atingir um nível, eu não diria mínimo não, mas um nível top de excelência. Eu acho que foi muito sucesso. Para vocês terem uma ideia, aí a gente teve quase 500 acessos, teve dia que teve quase 500 acessos ao YouTube, né, Bruno? A gente estava olhando aí, então, assim, isso é realmente qualidade. Olha que a gente está competindo com SCCV, né? Eu acho que está rolando agora também, né? E outros, e tem mais um outro evento que eu acho que a gente está competindo também. Tá?
Em relação ao ano passado, né, teve bastante presença de convidados internacionais, né? Pelo menos em relação ao ano passado que a gente participou no formato online, né? Gente do México, teve gente da Alemanha, inclusive, publicando com a gente aqui. Né?
Isso, eu ia ressaltar isso agora. A gente teve presença de muito mais pessoas fora do Brasil. Na verdade, eu deveria estar falando em inglês aqui, não sei se tem alguém de fora, acho que não. Não é? Mas tudo bem, vamos lá. A gente teve Alemanha, México, Uruguai, Peru, eu acho que Argentina também, né? Se não me engano. Quer dizer, teve presença de muito mais pessoas da América Latina e de fora da América Latina também, né? Dos Estados Unidos, acho que teve alguém que está lá agora também, e tem mais um outro país que eu não me lembro, que eu olhei lá. Mas o Bruno tem esse levantamento direitinho, deve colocar mais tarde na plenária isso. Então, assim, só agradecer mesmo, de coração, dizer que todo mundo que está aqui na Natalnet, e não só na Natalnet, no IFRN, na UERN, né, que é a estadual, deram o máximo de si, e o pessoal também das instituições que estão junto com a gente, que é a UFPR, né, a UTFPR também, né, e tem mais uma,
UFPB.
Isso.
A FEI do professor.
E a FEI, do Danilo, né, que são as instituições que estão por detrás aí, tanto da organização quanto do comitê de programa, né. Agradecer imensamente às instituições, né, que liberaram esses professores para que eles pudessem aí dar o máximo de si para a gente organizar o LARS, o SBR, o WRE, o WTDR, CTDR, né. E assim, dizer que a gente está maravilhado agora. A gente vai dar um break, um tempo, deixar outras instituições organizarem, né? Mas talvez no futuro o pessoal se anime aí novamente, né, Bruno? A fazer a versão presencial do evento. O pessoal já está animado com outro evento que provavelmente vem para cá, que é o CIBGRAP, SVR e SB Games também, né, nesse ano que vem. Mas a gente está aqui de corações abertos e esperando vocês, assim que acabar a pandemia, realmente para ter uma coisa presencial. Não agora, mas talvez em 1 ou 2 anos, né, após a Bahia organizar e a FEI agora nesse ano que vem, né? Ano que vem vai ser na FEI, já adiantando, quer dizer, a gente vai bater o martelo hoje à noite, mas eles são o único candidato, né? Houve um problema pela troca de comando, o Exército sempre ocorre troca de comando, e a troca de comando não favoreceu a ocorrência, a pandemia e troca de comando não favoreceu a ocorrência no Rio em 2022. E aí o pessoal, a gente até tentou contornar, mas no final não teve jeito. E aí a FEI se prontificou a organizar, então já convidar todo mundo para o ano que vem, está em São Paulo, São Bernardo do Campo, né? Curtindo lá calorzinho, talvez, nessa época, ou a Terra da Garoa lá, né? Chove um pouquinho, mas é bem legal. A gente já fez lá em 2010, lembrando, né? Foi um sucesso, foi na época, deu um up nos eventos, e com certeza vai ser um sucesso novamente. Desejar aí para o pessoal que está organizando lá muito sucesso no ano que vem. E agradecimento de coração. Vai lá, Bruno, é com você.
Beleza, Luiz Marcos, muito obrigado. Bom, só queria me despedir do resto do pessoal todo, né, que ficou com a gente até esse momento. Vou me despedir em inglês também, mas agradecer a todos, o pessoal que nos ajudou com a operacionalização do evento, né, o pessoal do laboratório, muito obrigado a todos, sempre nos dando força, a todos os autores que submeteram, a todos os palestrantes, todos os revisores de artigos, todos os colegas que coordenaram sessões técnicas, O evento não poderia ser feito sem vocês, então a gente agradece demais pela ajuda. E, bem, vamos ter essa reunião às 19 horas, né? O professor Eduardo Totti está com a gente no comitê do programa, o professor Tiago Nascimento está com a gente no comitê do programa. Agradeço também a todos eles. Eu não conseguiria fazer o mesmo trabalho sem o apoio deles. É bem trabalhoso, então a gente se dividiu bem aí. Eu acho que ficou legal. Acho que valeu a pena o esforço. Com certeza vale a pena, né, quando a gente vê o evento sendo realizado. E aí eu passo a palavra para o professor Eduardo Totti, que quiser falar alguma coisa.
Então, queria só cumprimentar todos vocês, em especial aí ao Bruno, ao Júlio, ao EDM, incansáveis aí em conduzir a maior parte das atividades, mas a todos e todas que estão por aqui e os que já se desconectaram também. Olha, foi sensacional o LARS, tá? Acho que dentro do que a gente consegue fazer de um evento remoto, tá dominada a tecnologia, está master no tema, mas eu sinceramente espero que a gente tenha aquela grande alegria de estar todos juntos na FEI no ano que vem, então, tá? E cumprimentos mais uma vez a todos e todas aí.
Obrigado, Todd. So back to English, just to say goodbye to everyone. It was very nice to have you here during this week. I would like to thank all the reviewers, all the support team that was with us during this week. Professor Eduardo Todd, Professor Tiago Nascimento from the program committee. All the people that was chaired during the session, during the technical sessions of the event, all the keynote speakers, Professor Wolfram Bugard, Professor Rudiger Dielman, Professor Carmen Torres, Professor Flávio Tonindadel. We would like to thank all of you to make this a great event, in my opinion, in the opinion of others too. So that is it. Anyone else want to say something? So no. This is it.
Well said, man.
We like to see you all in LARS 2022 next year, probably in São José dos Campos, right? So see you there.
São Bernardo dos Campos.
São Bernardo dos Campos. Sorry, in São Bernardo dos Campos. Sorry. So see you there. Ciao.
Ciao. Thanks.
Ciao, Bruno. Many thanks.